Section 1 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Amy Graymore. The Elements of Botany by William Ruskenberger. Lesson 1. Botany. Definition of plants, structure of plants, nomenclature of organs. Botany, formed from the Greek word botane, a plant, is that division of natural history which treats of vegetables. The science of botany is divided into three branches, namely, the anatomy of plants, vegetable physiology, and descriptive botany, which last comprises the classification of plants and their especial history. Botany therefore does not consist, as is commonly imagined by the ignorant, in merely getting by heart a great number of names of plants and of being able to apply their names to the objects to which they belong, but in a knowledge of the plants themselves, of their organization, their growth, their manner of living, their properties, and the relations they bear to each other, as well as the characters by which they are distinguished from each other. Definition of plants. Plants are beings organized for living, but they are not endowed, like animals, with the faculties of sensation and of performing voluntary motion. Like animals, these beings are readily distinguished from inorganic bodies by their mode of structure, by their nutritive function, through the means of which their substance is renewed and augmented by their origin, and by the limited duration of their existence. They differ from animals not only in being destitute of the functions of relation, but also in many other respects. Almost all vegetables live fixed in the soil. They absorb from without nutritive matters, which they assimilate without previously digesting them, and they have nothing which resembles a stomach. By the act of respiration, they possess themselves of the carbonic acid of the air and exhale oxygen. We have said that vegetables are destitute of the faculty of sensation, and the faculty of performing voluntary motion. This is very evident in an immense majority of instances. But there are some plants which, at first sight, seem to form an exception to this rule. For example, the branches and leaves of all plants are directed to that side from which come the light and air. Certain plants on the approach of night or the morning dawn close their leaves or flowers, and there are some that contract themselves in this manner when they are touched by any foreign body. The small shrub called the sensitive plant exhibits this phenomenon in a very remarkable manner, and a plant of certain Carolina marshes, Venus flytrap, Dionea muscipula, performs these motions most singularly. The leaves, which are formed of two lobes, are so irritable that they close on the slightest touch. When an insect alights upon the internal face of one of them, the two lobes immediately approximate each other, and the animal caught upon the thorns with which these lobes are armed dies in this species of natural snare. The rosalis, the white flowers of which often deck the pools in France, are somewhat analogous, for the hairs which fringe their broad round leaves lie down the moment they are irritated by the contact of a foreign body. But these phenomena differ essentially from the voluntary movements of animals. There is no proof that the plants we have just mentioned experience sensations, nor that the motions performed by them are directed by will. Sometimes these movements result from the action of heat or humidity upon certain parts of their tissues, and at other times they can only be compared to the automatic movements which are readily brought about by means of electricity or galvanism in animals that have been recently killed and deprived of the functions of relation. Of the structure of plants in general. Although plants differ very widely from each other in their external forms, they closely resemble each other in the materials of which their organs are composed. If we examine the internal structure of plants by the aid of a microscope, we find they consist entirely of cellular tissue alone, or at most of cellular tissue united to vessels. Plants that are composed entirely of cellular tissue are called cellular plants, and those formed of cellular tissue and vessels are named vascular plants. Of cellular tissue. The cellular or utricular tissue of vegetables consists of a multitude of vesicles, minute cells, filled with a liquid or other substance, Sometimes these little bladders are rounded and loosely attached to each other, but in general they are so strongly pressed against each other that they are flattened at the points where they touch and take the form of polygons, from the Greek polis, many, and gon, sides. At the same time, their union becomes so intimate that it is difficult to separate them, and the cells formed by their cavities seem to be separated only by simple partitions, as cavities would be if hollowed out of a continuous or solid mass, like the cells of a honeycomb, for example. The form of these cells varies very much. Sometimes they are spherical or octagonal, at other times flat or very much elongated, and tapered at their extremities like spindles. In the latter case they are often designated under the name of claustras. Their surface frequently presents rays or points which resemble pores, but in reality these vesicles are completely closed and are without openings or orifices. Their parietes are naturally transparent and almost colorless, but ordinarily these cells contain granules, which are deposited on their internal surface, and when these corpuscles, little bodies, are green, brown, red, etc., their parietes appear to be colored in the same manner. The color of different parts of plants depends upon this circumstance. The cellules, little cells, of the cellular tissue often have between them empty spaces of more or less extent, called intercellular meatus, or intercellular pores or passages. These cavities, which are of a regular form, are very important, as we shall see in the sequel. Of vessels. The vessels of plants are generally cylindrical tubes, which somewhat resemble excessively elongated cells. They differ very much in their structure, and they are divided into tracheae, false tracheae, punctuated or dotted vessels, maniliform vessels, reticular vessels, mixed vessels, and proper vessels. Tracheae. We give the name of tracheae to tubes which closely resemble the tracheae of insects, for like them they are formed of a thread spirally folded. This thread, which is silvery white, is very elastic and easily unrolled, and if we carefully break a leaf of a rose tree or dogwood, for example, we find the two fragments united to each other by filaments, similar to spider's web, which are in fact the unrolled tracheae. Sometimes, instead of being formed of a single spiral thread, these vessels are composed of 2 or 3 parallel threads rolled together. Their length is in general very considerable, and it seems that they terminate in a point at each extremity. They do not branch or ramify like blood vessels in animals, and ordinarily they are united in bundles. The false tracheae, which are also called annular or radiated vessels, are unramified tubes, marked by transverse parallel rays. When the rays are very close together, these vessels resemble tracheae very much, but they are not elastic and cannot be unrolled. The punctuated or dotted vessels are cylindrical tubes like the preceding, but their parietes are dotted with small opaque points arranged in parallel or oblique series. They were formerly called porous vessels, because it was believed that these dots were holes, but we are now assured that they are not pores. The reticular vessels are cylindrical tubes, the surface of which, being covered by oblong transverse spots, gives them the appearance of a net. The mixed vessels are tubes which at different points in their length seem to possess alternately the characters of the 3 kinds of vessels we have just mentioned. The maniliform, or bead-like vessels, are punctuated tubes which ramify and are contracted or strangulated at different points. Many botanists suppose they consist of series of cells attached to each other end to end. The proper vessels are cavities which are sometimes in the form of short, blunt tubes, and sometimes they are elongated very much. They enclose the particular juices of the various species of plants. Finally, the vessels of the latex are ramified canals, which may be considered as a sort of proper vessels. According to some botanists, they are lined by a proper membrane, but according to other observers, they have no lateral parietes and are merely intercellular passages, or meatus. Of the compound constituent parts of organs. The elementary parts of plants we have just mentioned constitute, either alone or by their union, the tissues and the different organs, which in their turn concur in the formation of the various apparatuses constituting the body of these beings. Such are the fibers, the epidermis, the hairs, the glands, etc. Fibers, the fibers which are often found in the different parts of plants, but chiefly in the stems, are not composed of a peculiar tissue, but are formed of vessels united in bundles, intermingled with elastras or elongated cells. Among these vessels we sometimes find tracheae, but most of them are punctuated vessels. The filaments thus formed are arranged parallelly, and joined together by a more or less loose cellular tissue. It is therefore much easier to separate them lengthwise than transversely. Epidermis, from the Greek epi, upon, and derma, skin. The epidermis or cuticle is a thin membrane which covers the external surface of plants. It is especially distinct in the young stems, the leaves and roots. It is composed of cellular tissue, the cells of which adhere more strongly to each other than to the subjacent parts, and for this reason it is, in general, easily raised up. We often remark in it little openings called stomata, from the Greek stoma, mouth, which are not visible without the assistance of a magnifying glass. The edges of these pores are formed by two oval or globular cells, filled with green globules, and their opening corresponds with the intercellular vacuities or lacunae, the uses of which appear to be very important in the respiration of plants. No stomata are found upon the roots. Many cellular plants, such as mushrooms and mosses, are altogether without them, and they are also wanting in certain plants that live in water. The hairs of plants are external appendages, formed of elongated and projecting cellules. Sometimes they are simple, that is, composed of a single cell. Sometimes they are partitioned, that is, formed of several cells arranged in a row, end to end, and at other times they are more or less branching. Sometimes they lie upon glands, and serve as an excretory canal to the caustic juices secreted by these organs. Hairs vary extremely in length, density, rigidity, and other particulars. On this account they have received the following names: down or pubescence, when they form a short soft layer which only partially covers the cuticle or epidermis. Hairiness, hirsutus, when they are rather longer and more rigid. Pilosity, pilosis, when they are long, soft, and erect. Villosity, villosus, when they are very long, very soft, erect, and straight. Criny, crinitis, are this variety in excess. Velvet, velutinous, when they are short, very dense and soft, but rather rigid, and forming a surface like velvet. Ciliae, eyelashes, ciliatus, when long and forming a fringe to the margin like an eyelash. Bristles, setae, setosis, when short and stiff. Stings, stimuli, stimulans, when stiff and pungent, giving out an acrid juice if touched, as in the nettle. Glandular hairs, pillae capitati, when they are tipped with a glandular exudation. Hooks, hami, unci, rostella, when curved back at the point. Barbs, glochis, glochidatus, if forked at the apex, both divisions of the fork being hooked. Scurf consists of thin, flat, membranous discs with a ragged margin, formed of cellular tissue, springing from the epidermis. It may be considered as a modification of hairs, for it differs from those bodies only in being more compound. Prickles are conical hairs of large size, sharp-pointed, and having their tissue very hard. They differ from thorns in being fixed to the bark. The thorn is fixed to the wood. Glands. We give the name of glands to those organs which are destined for the secretion of particular liquids. They are found in almost all parts of plants. They are small cavities, sometimes formed of cellular tissue only, and sometimes of very little cells mingled with a great number of vessels. In other respects they do not appear to differ essentially from the tubiform reservoirs we have already mentioned under the name of proper vessels. Classification of the organs and functions of vegetables. The functions of vegetables are referred to two classes. One belongs to the individual life of the vegetable, that is, the functions which affect its nutrition. The other refers to its multiplication, or the preservation of the species. The parts of the plants that serve the functions of nutrition are the roots, the stem, and the leaves. The parts which are especially designed to secure the multiplication of plants are the organs of fructification, namely the flowers and fruits. End of Lesson 1. Section 2 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Botany by William Ruskenberger. Lesson 2. Functions of Nutrition. Absorption and ascent of sap. Roots, their structure and forms. Stems, its divisions, varieties, etc. Structure of the stem and exogens. Medullary canal. Pith. Medullary sheath. Wood. Medullary rays. Bark. Epidermis. Cork. Structure of the stem and endogens. Functions of nutrition. The phenomena of the life of nutrition in plants are referred to 5 distinct functions, namely, first, the absorption of nutritive matter. Second, the transportation of the nutritive liquid or sap to the organs of respiration. Third, the process of respiration and elaboration or preparation of the nutritive juices in the interior of the respiratory organs. Fourth, the transportation of the sap thus elaborated to different parts of the plant, and the deposition or assimilation of its elements in its various parts. Fifth, the secretion of peculiar juices affected by special organs. The roots of plants absorb the nutritive matter necessary for the maintenance of vegetable life, and the liquids, thus introduced into the body of the vegetable, constitute what is called the ascending sap. This sap rises through the stem by means of particular canals, and in this manner reaches the leaves and other green parts of plants. There it is modified by the effects of transpiration and of respiration, and after having been thus prepared, the sap descends, following a new route, and is distributed to those parts for the growth of which it is destined. We will study successively these phenomena and the organs which are the seat of them, both in vascular and cellular plants. Of the absorption and ascent of sap. The absorption of nutritive matters is principally effected by the extremity of the roots, and by passing through these organs and mounting along the stem, they reach the leaves, in the substance of which the alimentary juice is rendered fit for the nutrition of the plant. These two phenomena, the absorption and ascent of the sap, are very intimately united, and in order to understand them, we must in the first place study the structure of the two portions of the plant which are the seat of them, namely the roots and stem. Of the root or descending axis. Radix. We give the name of root to that inferior portion of plants which serves to fix them in the soil, and which, by its growth, increases in length in an opposite direction to the stem. With the exception of some plants that live under water or float upon its surface, all vegetables are provided with roots, and these organs are almost always buried in the earth. Sometimes the roots float freely in the water, and there are some plants that insinuate them into cracks in walls or in crevices of the stem of some other plant, as the mosses, for example. There are certain plants the roots of which arise at a considerable distance above the surface of the soil, and have only their extremity buried in the earth, so that the greater part of their length remains exposed to the air. To such roots we give the name of aerial or adventitious roots. The maize or Indian corn and many other American plants have them. We see now that it is not a constant character of roots to be covered up in the earth, and on the other hand, we should be equally deceived if we were to regard as roots all parts of plants that are buried in the soil, for it sometimes happens that the stem, instead of rising up through the air, creeps horizontally underground. But the structure of the two parts is different and prevents them from being confounded with each other. The tissue of roots is whitish, and never becomes green by exposure to the action of light, which occurs to all other parts of plants. Those stems which creep along under the ground are called rootstocks, or subterranean, or rhizome, from the Greek rhizza, root. Stems. The stems of the orris root, ginger, and potato, upon which grow the tubers we eat, are instances of this kind. The root, considered as a whole in general, consists of three distinct parts. First, the body or middle part, which is sometimes globular, and at others similar in form to a descending stem. Second, the radicles, the more or less delicate fibers which terminate the root at its lower part. And third, the neck or column, the point that separates it from the stem, and which is often marked by being smaller. The internal structure of roots varies. In general, it is divided into the cortical part, or bark of the root, and central or ligneous part. The bark of the root, which is often very thick, is entirely composed of cells. Its epidermis is always without stomata. The ligneous body of the root is not ordinarily composed of distinct fibers, and we do not find tracheae in it, as in the stalk or stem of vascular plants. Nor has it pith in the center. The extremities of the radicles are unprovided with epidermis, and are composed only of rounded cellular tissue. These parts are called spongioles, little sponges, and, as we shall presently see, play a very important part in absorption. The general forms of roots varies much, and gives rise to numerous distinctions, the chief of which are the following. Division of roots. Roots are primarily divided into simple and compound or multiple roots. Simple roots have a single base continuous with the stem. They are called taproots when they descend perpendicularly, and have almost the whole of their spongioles united at their extremity. These are fusiform when they are shaped like carrots, and napiform, tuberous, etc., when they are swelled and rounded like turnips. Fibrous when they are very branching and ordinarily furnished with numerous spongioles. These are knotted when they present swellings along the course of their fibers, and creeping or repent when they run along near the surface of the soil. The second primary division of roots is the compound roots. They arise in great numbers from the neck of the plant. They are said to be branching or capillary, when each fiber, which is distinct at its origin, gives off branches in abundance. Knotted when the fibers have swellings or knots in their course, and fusiform or fasciculate when they are formed by the union of a great many more or less elongated tubercles. We may add that roots are said to be fleshy when they are more succulent, juicy, and larger than the base of the stem, and ligneous when their tissue resembles wood. They frequently present swellings or tubers, which are always masses of nutritive matter destined to supply the wants of the plant at a certain period. Finally, we give the name of adventitious roots to those which in certain instances arise from the stem, but are in other respects analogous to ordinary roots. Of the stem, caulis. We give the name of stem, caulis, stalk, to that part of plants which is intermediate between the roots and the leaves. The stem grows in an opposite direction to the root, and seeks the air and light. In general, it rises vertically above the soil, and serves to support the leaves, flowers, and fruit. Generally, this part of a vegetable is very apparent and easily recognized. Sometimes it is simple, at others branching, and when it is simple below and branching in its superior part, the first part is called the trunk, and to the second we give the name of branches. All vascular plants are provided with a stem, but sometimes it is so short and so enveloped in leaves, or so completely hidden in the ground, that it seems not to exist. Vegetables thus formed are called acaulis plants, from the Greek a, without, and caulis, stem or stalk. But this absence of the stem is only an appearance. Thus in tulip and other bulbs there exists, amidst the leaves, in form of scales, of which the greater part of these bodies is composed, a tissue which separates these appendages from the roots, and which constitutes a true stem. Only instead of being elongated and cylindrical, as is ordinarily the case, it is generally globular and flattened above, an arrangement which has procured for it the name of cormus or plateau. Subterraneous or rhizome stems have the appearance of roots, but are distinguished from them by their structure and several other characters. Their tissue becomes green by the action of light, which is never the case in true roots, and under the influence of moisture, branches spring up covered with leaves, but radicals never grow from them. Sometimes these subterraneous stems bear, here and there, irregular tubercles. The stem of a plant assumes numerous and very different appearances in different plants. If above ground, it is root-shaped or knotted, ascending, creeping, articulated, leafless, succulent, and deformed, or leafy. If it bears the flowers proceeding immediately from the soil or near it, it is escape. The stems in most plants rise vertically in the air, but sometimes it wants strength to sustain itself and rests drooping on the surface of the ground, to which it often attaches itself by roots. Stems of this kind are named reapant or creeping, or they sustain themselves upon some other more robust plant, as is seen in the climbing plants, etc. It is observed that the latter often wind themselves spirally round whatever supports them. They are then called twining or voluble, and it is worthy of note that the direction according to which different individuals of the same species wind themselves never varies. In some, such as the haricot or bean and bindweed, it is from right to left. In others, such as honeysuckle and hop, it is constantly from left to right. While young stems are always of a soft consistence and similar to grass, they often remain in this state and live but a year. They are then called herbaceous stems. In other instances they acquire more or less hardness, their interior is transformed into wood, and they live out of the ground many years. In this case they are called ligneous stems. When the stem, although it be persistent, remains watery and more or less soft, it takes the name of fleshy stem. We generally apply the name of shrub to those plants with a ligneous stem, which branch at their base and do not much exceed a man in height, such as the rose or lilac, and we give the name of tree to those with a ligneous, woody stem that branch only at the superior part and rise to a considerable height. The branches are only divisions of the trunk which diverge more or less from it, and are again subdivided in their turn. Upon their arrangement depends the general form of the plant. Sometimes they stand up, which gives the tree a pyramidal form. Sometimes they are spread out, and at others they are pendant or hanging. Certain stems present at intervals knots or enlargements, produced by an induration and a swelling of their tissue. When they are also hollow internally, they are designated under the name of culm or straw. The stems of wheat, barley, and oats are of this kind. We give the name of stipe to stems which resemble a round column, as large above as below, and crowned with a cluster of leaves or flowers like the stems of palms. The stem of all vascular plants is composed of fibers arranged in bundles, vesiculae, or layers, and variously surrounded by cellular tissue. But we observe very great differences in their structure, and these variations, which coincide with differences not less important in their mode of growth, have caused vascular plants to be divided into two groups, namely exogens and endogens. Exogens. Exogenous plants, from the Greek ex, from, and genome, I grow. A term applied to those plants, a transverse slice of whose stem exhibits a central cellular substance or pith, an external cellular and fibrous ring or bark, and an intermediate woody mass, and certain fine lines radiating from the pith to the bark through the wood and called medullary rays. They are called exogens because they add to their wood by successive external additions, and are the same as what are otherwise called dicotyledons. They constitute one of the primary classes in which the vegetable world is divided, characterized by their leaves being reticulated, their stems having a distinct deposition of bark, wood, and pith, their embryo with two cotyledons, and their flowers usually formed on a quinary type. Endogens, endogenous plants, from the Greek endon, within, and genome, I grow. One of the primary classes of plants, so called because their stems grow by successive additions to the inside. They are usually known by the veins of their leaves running parallel with each other, without branching or dividing. Grasses, lilies, the asparagus, and similar plants belong to this class, which in warm countries contains trees of large size, such as palms and screw pines. The class of exogens comprises all the trees and shrubs of our forests, and is composed of vascular plants, the stem of which has a medullary canal in the center and grows by superposed layers. The class of endogens comprises those plants in which the stem has neither a central canal nor concentric layers. The palms belong to this division. Structure of the stems of exogenous plants. In the stems of these plants we distinguish two principal parts, the bark and the central or ligneous part, which might be called the body of the stem. Each one of these portions is in turn composed of several different parts. The central portion of the stem is formed by a central pith, by ligneous layers, and by medullary rays. The bark or cortical portion is composed of the epidermis of a cellular envelope, and of a fibrous part called liber or cortical layers. Liber, Latin, bark, is the interior lining of the bark of exogenous plants. If we cut through an elder or any other exogenous tree transversely, we observe in the center a canal which is ordinarily angular or very nearly cylindrical, and which in the young branches, if not in the whole plant, is filled with a round cellular tissue. This cavity is called the medullary canal, and the cellular tissue found in it is named the pith of the plant. The central pith is of a soft consistence and of a very homogeneous structure. Homogeneous, from the Greek homo, together, in genus, kind, of the same kind. Bodies whose constituent elements are of one and the same kind are said to be homogeneous. While young it is always humid and of a light greenish tint, but with the progress of age, the cells of which it is composed become empty, dry, and assume a remarkable whiteness. Sometimes it is torn by the effect of the elongation of the stem, and separates in laminae or bundles, as may be easily seen in branches of jasmine that have attained 1 year old. In herbaceous plants and in ligneous plants of very rapid growth, such as the elder, the space occupied by the pith is very considerable. But in trees, the wood of which is very hard, such as oak, the medullary canal or sheath is generally very small. The parietes of the canal, containing the central pith, called medullary sheath, are formed of longitudinal fibers, ordinarily arranged in a circle, and of a layer composed of tracheae, false tracheae, and porous vessels. It is the only part of the stem in which true tracheae have been observed. Between the medullary canal and the bark is the ligneous body or wood, which is composed of concentric layers, the number of which is more or less considerable according to the age of the plant. Each of these layers is composed of longitudinal fibers, united to the subjacent layer by cellular tissue. These fibers are formed nearly in the same manner as those of the medullary sheath, except that no tracheae are found in them. They are composed only of clusters, or elongated cells, or dotted or rayed vessels. The ligneous body constitutes what is generally termed wood. Its central portion is harder than its external part, and is ordinarily of a different color. It is this part which is commonly called the heart of the wood, and which botanists designate under the name of true wood, heartwood, or duramen, while they give the name of alburnum or sapwood to the external ligneous layers, the solidity of which is less and the color whiter. In other respects the structure of these parts is the same, only the ligneous fibers of the true or perfect wood are filled with solid matters deposited in their interior, while the proportion of liquids is more considerable in the sapwood or alburnum. In trees of slow growth, the line of demarcation is very distinct between the heart and sapwood, and in the colored woods, such as ebony, mahogany, etc., it is the heart only that possesses their peculiar color, the sapwood being usually white. In trees of very rapid growth, such as the poplar, willow, etc., there is, on the contrary, but little difference between these two ligneous layers. As we shall see in the sequel, the alburnum is gradually converted into perfect wood, and it is by the formation of new ligneous layers between those already formed in the bark that the stem increases in thickness. The medullary rays are the divergent lines which run from the center of the stem towards its circumference. They are composed of vertical laminae of compressed cellular tissue, and are very analogous to the pith from which they seem to arise. These rays come in part from the external ligneous layers and terminate in the bark, thus establishing a communication between the superficial and central parts of the stem. The bark is composed first of a layer of cellular tissue, which constitutes the epidermis, and of a deeper layer formed of clusters grouped together so as to form fibers, but without being united with tracheae. In the progress of age, new alternating zones of cellular tissue and fibers are formed beneath the preceding, and there results from it a series of superposed layers which resemble those of the wood, but differ from them essentially in their mode of growth. We have observed that the latter are formed successively, one on top of the other. In the bark, on the contrary, growth takes place from without inwards. We give the name of liber to the inner layers of the bark because they are easily detached in thin plates or laminae, and because the ancients made use of it, as we do paper, to write upon. Note: some of our young readers may remember the Latin word liber, and its several versions, given as follows: liber book, liber tree, liber child, and liber free. The external layer of cellular tissue constitutes the epidermis, and is what botanists term the herbaceous envelope of the bark. In the course of the growth of the subjacent parts, it soon becomes strongly compressed, and at a certain epoch we see it crack and tear in flexible laminae, or detach itself in scales or patches. The neighboring cortical layers undergo the same alterations, and when the part of the bark thus modified has been raised up, the lamina of cellular tissue thus exposed becomes for a brief period a kind of epidermis, until it is itself in turn detached. For this reason the thickness of the bark is never very considerable, and its surface is continually renewed. In some plants the herbaceous layer becomes very much developed, and the portion of bark that is thus separated is of sufficient consistence and thickness to be very useful to us in the arts. Cork, for example, is the only superficial part of the bark of a particular species of oak, Quercus robur, which detaches itself from the liber every 8 or 9 years, and it may be removed more frequently without any danger of destroying the tree. Bark often contains in its interior cavities which are reservoirs of proper juices, and in particular those called the vessels of the latex. Latex is a peculiar fluid, usually turbid, and colored red, white, or yellow, often, however, colorless. Structure of the stem of endogenous plants. The stem of these plants, that of a palm for example, is formed of a considerable mass of cellular tissue, analogous to pith, through which penetrate bundles of fibers in various ways, but never forming concentric layers, as in the exogenous plants. Each of these fibers is composed of elongated cellules, of large dotted vessels, of tracheae, of proper vessels, and of polyhedral cells. They are closer together near the center of the stem than towards its circumference, and their superior extremity is abruptly curved outwards, to be continued into leaves. It is remarked also that in general there is no distinct bark, and that the external pellicle never grows in layers, as is the case in exogens. Cellular plants never present parts that are really analogous to the organs we have just spoken of, and to which we shall again recur. End of Lesson 2.
Section 3 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Botany by William Ruschenberger. Lesson 3, Part 1. Lesson 3. Mechanism of the absorption and ascent of the sap. Ascending sap, exhalation, respiration, leaves, parts of leaves, their structure, shape, and position, stipules, tendrils, examples of the forms of simple and compound leaves, exhalation, respiration, distribution of the nutritive juices, descending sap, secretions, excretions, succession of crops, proper juices, lignin, fecula, growth of plants, grafting, effects of the seasons on the nutrition of plants, the age of plants. Mechanism of the absorption and ascent of the sap. 1. It is by the process of absorption that plants derive from the soil in which they are fixed the nutritive matters necessary for their growth and the maintenance of their existence. 2. The nutritive matters, to be pumped up in this manner, must necessarily be in a fluid state. In the solid form, they could not be absorbed, and it is in fact water holding various substances in solution that thus penetrates the plant and serves for its nourishment. 3. It is chiefly, and sometimes exclusively, by the extremity of the roots that this operation is effected. The epidermis, which covers almost the whole plant, in general offers obstacles to the passage of these liquids. But the spongioles, as we have already seen, are unprovided with this envelope and constitute a cellular tissue which gives a ready passage to water. For this reason, we must consider these spongioles as the chief organs of absorption. 4. Some plants also absorb by the leaves, and when the stem of a plant is cut across, its internal tissue, being thus laid bare, also pumps up water in which it may be placed. But in the ordinary state of a plant, these cases are exceptions, and the absorption of liquids is carried on in the most active manner by the spongioles. 5. It has been remarked that water, rendered thick and viscid by the presence of foreign substances, was absorbed very slowly and with difficulty. But, when its fluidity is not diminished by matters that it holds in solution, it penetrates vegetables just as if it were pure. Now, the water which reaches the roots of plants always holds in solution a greater or less quantity of air, earthy salts, and organic matter, and consequently it introduces these subjects into the interior of the plant, which is either benefited or injured according as they are proper for its nutrition, or as they exert an injurious influence upon its organs. 6. The liquids thus absorbed by the roots constitute the ascending sap, which rises through the stem to reach the leaves. 7. The ascent of the sap is always effected through the ligneous body, and it is remarked that it takes place more actively through the alburnum than through the perfect wood. 8. It is not known with certainty by what way the absorbed liquids rise up in this manner. Many botanists think that it is only by the intercellular passages. Others believe that it is by the vessels. And in fact, if we place the roots of a plant in colored water, we are not long in perceiving that the vessels of the stem assume the same color, which seems to indicate that it is through these tubes that the liquids mount up toward the leaves. Nevertheless, under ordinary circumstances, we find these vessels empty, or at least filled with air, and it would seem that it is chiefly through their interior that the air absorbed by the roots rises in the stem of the plant. 9. The rapidity and force with which the ascent of sap takes place are sometimes extremely great. In the experiments made upon this subject, it has been shown that a branch of an apple tree cut across and surmounted by a tube raised water contained in the latter several feet in the space of some hours. And what are called vine tears is nothing but the ascending sap which escapes in abundance when the plant is trimmed. In other experiments made to ascertain the force with which the sap mounts in the grapevine, it was found to be sometimes so great as to sustain the weight of a column of water over 40 feet in height. 10. The circumstances that have most influence upon the ascent of sap are heat and light. Of exhalation and respiration. 11. To render it fit for the purpose of nutrition, the ascending sap undergoes in the interior of the plant considerable changes. These changes are the result of two important phenomena, namely, exhalation and respiration. 12. The leaves are the chief seat of these two functions, and must be regarded as their special organs. We will now study their structure. Of leaves. 13. The leaves of vascular plants are the lateral appendages of the stem, formed of more or less distinct fibers and cellular tissue, enclosing in its interior a great deal of green coloring matter. 14. The fibers of the leaf are the continuation of those of the stem, but ordinarily they contain more trachea. In general, they form at first a cylindrical fasciculus bundle, caniculated, that is, hollowed in a gutter on the opposite side, or laterally compressed, which is named petiole, or leaf stalk. Then they expand and join again to form the flat part called the blade or limb of the leaf. When the fibers separate immediately on springing from the stem, the leaf has no pedicel or petiole, and it is then said to be sessile, from the Latin sedio, I sit. The petiole of dicotyledonous plants is separated from the stem by an articulation or joint, that is, a line at which its tissue offers but little resistance, the cells and vessels of which it is composed being placed end to end, instead of being mingled as usual. It is on account of this arrangement that the leaves fall when they fade, while those of which the limb or blade rises directly from the stem are destroyed only little by little and remain adherent at their base. The first are called caducous or articulate leaves, and to the second we give the name of persistent. The leaves of fir trees are persistent. 15. When all parts of the leaf are equally adherent to each other, it is named a simple leaf, whatever may be the divisions of its blade. For example, the leaves of the lilac, the ranunculus, of the vine, etc. See figures 17 to 57. Sometimes the same tail or peduncle supports several petioles, each of which is articulated upon this peduncle, as it itself is upon the stem, and then this assemblage is called a compound leaf. Examples of compound leaves are seen in the sensitive plant, the leaves of the acacia, of the chestnut, etc. See figures 58 to 74. 16. The fibers, by expanding the limb, constitute the nerves of the leaf, and the cellular tissue lodged between these bundles of fibers, thus ramified, constitutes the parenchyma of the leaf. 17. The form of the leaf depends primarily upon the disposition of the nerves. In general, the nerves expand on a single plane, so as to form a plate or membrane with two surfaces, a superior and an inferior. But they sometimes ramify in all directions, and then give rise to leaves characterized by being thick, cylindrical, triangular, or swelled, as we observe in certain fleshy plants. The large nerves that arise immediately from the petiole are called primary nerves, figures 25 and 26. Those which arrive from the latter are secondary nerves, figure 28. We sometimes give the name of tertiary nerves, figure 43, to those ramifications which spring from the secondary nerves, and we apply the name of veins of the leaf to those terminal divisions of the nerves which are visible to the eye, but too small to make any projection on the surface. The veins are merely a continuation of the nerves, and both are constituted of the same fibers and vessels. It must not be supposed from the names that have been arbitrarily given them that these parts are similar in function to those parts of animals of the same name. 18. Sometimes the leaf presents one or more primary nerves which diverge in a straight line from the base of the blade and give rise to more slender nerves that separate from each other, following a straight line and forming an angle with the first, figure 28. At other times, the principal nerves are curved from their base, figure 34. 19. We give the name of angular-nerve leaves to those in which the primary and secondary nerves are straight and form angles with each other, figure 26. And we call those curvy-nerve leaves in which the primary nerves are curved, figures 37 and 43. The first belong to exogenous or dicotyledonous plants, and the second to endogenous or monocotyledonous plants. Monocotyledonous, from the Greek monos, single, and cotyledon, seed lobe, applied to plants that have but one seed lobe or cotyledon in the embryo. 20. The angular nerve leaves present four principal arrangements. Sometimes they are penninerve, that is, provided with a middle nerve, called also midrib, which is a prolongation of the petiole, and which gives off to the right and left secondary nerves like the feathers of a pin. For example, the olive leaf, figure 22, the leaf of the yoke elm, and of the beech tree. Sometimes they are palminerve, that is, provided with several primary nerves, which separate from each other at the base of the blade, like the divisions of a fan, figure 28. For example, the leaf of the grapevine, which has 5 primary nerves, and that of the mallows, in which we count 7 or even 9. The number of these nerves is always unequal, and that of the middle appears to be the prolongation of the petiole, pelty nerve, figure 45, that is, provided with nerves that radiate on an oblique plane relatively to the petiole, so as to constitute a sort of disc or shield placed upon its peduncle, foot, for example, the leaf of the nasturtium. And in others again, they are pedally nerve, that is, having a very short central nerve or midrib, from which spring two largely developed lateral nerves, the ramifications of which are very small towards the external side, edge, of the leaf, and very strong towards the center of the blade, like the leaves of the fetid hellebore, figure 72, and some of the arums, for example. 21. The curvy nerve leaves, in general, have a great number of slightly projecting nerves, which at most generally ramify near their summit, and are often nearly parallel to the greater part of their length. For example, the leaves of the narcissus, ant fig, figure 37. 22. It sometimes happens that the space comprised betwixt the nerves is not filled by cellular tissue, which produces a very singular arrangement. The leaf is then full of holes and resembles a trellis work, for example, the leaves of Hydrogeton fenestralis, or the holes are irregular, as we see in the leaves of the Dracontium pertussum. 23. At other times, the cellular tissue which surrounds the nerves is spread out in such a way as to completely unite them to their utmost extremity, in which case the leaf is said to be entire, for example, the leaf of the lilac and of the olive, figures 22, 52, and 53. But between these two very different modes of conformation, there is a great number of intermediate degrees. Sometimes the parenchyma completely unites all the ramifications of a secondary nerve, but does not extend between the different nerves that arise from the primary nerve, so that the blade is divided into several segments or lobes. Sometimes these lobes are joined at the base, or as far as the middle of their length, and then the leaf is said to be partite or divided, and the intervals between the lobes are called fissures, figure 32. According to the number of these fissures or divisions, the terms trifid, quinquefid, etc. are used. In some cases, this junction is complete, but the parenchyma, which separates the last nerves, does not extend entirely to their extremity, and the edges of the leaf are then dentate, as in the rose, figure 47. When these small marginal divisions are rounded instead of being pointed, they are called crenulations, and the leaf is said to be crenulate, figure 41. 24. The two surfaces of the leaf are ordinarily covered with an epidermis, which often has hairs upon the nerves, and stomata on the parenchyma. These appendages and orifices are, in general, especially numerous on the inferior surface, and on this account it is almost always paler than the superior surface of the leaf. Sometimes there are no stomata on the superior surface, and the arrangement of the cells of the parenchyma is not the same as beneath. In the thickness of the leaf there are ordinarily cavities, or intercellular lacunae, which contain air and communicate externally through stomata, figures 9 and 10. Sometimes we also find in the parenchyma glands or reservoirs of the proper juices. Parenthetic remark. The distribution of the vascular tissue through the limb of the leaf is termed its venation or nervation, because the course of the vessels, of which these nerves are made up, have been supposed to bear some resemblance to the distribution of veins and nerves in certain parts of the animal structure. The bundles of vessels, constituting the nerves, maintain nearly a parallel course in their passage through the petiole, and are closely condensed together, but on arriving at the limb they separate, and as we have seen, are distributed in various ways. It will be observed that they may all be referred to one or other of two classes, called the angular nerve and curvy nerve arrangement. End of parenthetic remark. 25. The position of the leaves on the stem and branches varies in different plants, and furnishes very useful characteristics to botanists for the distinction of species. Sometimes they are opposite, that is, they rise in pairs at the same point from two sides of the stem or peduncle, figure 70. Sometimes they are verticulate, that is, grouped three or more together around the same part of the stem, and at other times they are alternate, that is, they arise separately at different points. 26. It is remarked also that opposite leaves are almost always so arranged that the different pairs cross each other. When they touch each other at the base, instead of arising from the opposite sides of the plant, they are called gemini or geminate leaves. 27. On the stems of many plants, we observe on both sides of the leaf small organs named stipules, which seem to be very analogous to leaves, but their nature is not fully ascertained. Figure 16, SS. They are only found in the dicotyledonous plants, and they sometimes resemble little leaves, at others scales. Parenthetic remark. Whatever arises from the base of a petiole or of a leaf, if sessile, occupying the same space, and attached to each side, is considered a stipule. The appearance of this organ is so extremely variable, some being large and leaf-like, others being mere rudiments of scales, that botanists are obliged to define it by its position and not by its organization. Stipules, the margins of which cohere in such a way that they form a membranous tube sheathing the stem, are called ochrae. Example, the rhubarb. Lindley. End of parenthetic remark. 28. The filamentous appendages, known under the name of tendrils, which twine themselves around neighboring bodies, serve to sustain weak and climbing plants, are frequently petioles or stipules, modified in a particular manner, but they are also often formed by the peduncle of flowers that have proved abortive in development. 29. According to their duration on the stem, the leaves are caduous when they fall early, as in the plane tree; deciduous when they fall before the new leaf appears, as in the horse chestnut and most other trees; marcescent when they wither before falling, as in the oak and many other trees; persistent or evergreen, sempervirens, when they remain on the vegetable one winter or longer, as the ivy, the pine, the myrtle, the common laurel, etc. Plants of this kind are called evergreens. The various shapes of leaves and the names given to them, as well as the variety of their margins, may be seen in the following. Examples of the forms of simple leaves. The side or edge of the leaf in which the petiole is inserted is termed the base, and the opposite extremity the apex of the leaf. A linear leaf, Folium lineare, figure 17, folium, Latin, a leaf, lineare, Latin, line-shaped. The two edges straight and equidistant throughout, except at the two extremities. The aster linearifolis, the starflower, as well as Indian corn and the grasses generally have leaves of this kind. When it embraces the stem, it is vaginate or sheathing. A subulate leaf, Folium subulatum, figure 18. Subulate from the Latin, subula and awl-shaped. Linear at bottom, but gradually lessening toward the top, and ending acute. The Phascum sebulatum, one of the mosses, and the jonquil have a leaf of this description. An acerose leaf, from the Latin acer, a needle, in the form of a needle, is seen on pines. It is linear acuminate. An obtuse leaf, Folium obtusum, figure 19, blunt pointed. The apex is broader than the base and forms the segment of a circle. The primrose has a leaf of this kind. An obcordate leaf, Folium obcordatum, figure 20. The Latin word ob is prefixed to technical terms to indicate that a thing is inverted. Obcordate means inversely cordate, see figure 51, the notch being at the apex instead of the base of the leaf. Example, Oxalis acetosella, sheep sorrel. An emarginate leaf, Folium emarginatum, figure 21. Emarginate, from the Latin e, from, and margo, margin or edge, notched, having a notch at the end. Example, the geranium emarginatum. When the notch or sinus is very obtuse, it is said to be retuse or almost emarginate. A lanceolate leaf, Folium lanceolatum, figure 22, lance-shaped, as in the olive, narrowly oblong and tapering to each end. The peach tree has leaves of this description. An acute leaf, Folium acutum, figure 23, sharp-pointed, terminating in an acute point without tapering suddenly. The Solidago odora, an aromatic plant, is an instance. A cetaceo acuminate leaf, Folium cetaceo acuminatum, figure 24, from the Latin ceta, a bristle. The point of the leaf terminated by the straight, bristle-like projection. The Quercus phellos, willow-leaved oak, is an example. Leaves are mucuronate, from the Latin mucro, in the genitive mucuronus, a sharp point, when an obtuse leaf terminates in a short, rigid point, formed by the projection of the midrib. Cuspidate, from the Latin cuspus, the point of a spear or other weapon, when it is more generally prolonged into a rigid point. Pungent, when it terminates in a hard, sharp point, like the leaves of thistles. Awned, aristate, from the Latin arista, a beard of wheat, when it terminates in a long, hard bristle or beard. An acuminate leaf, Folium acuminatum, figure 25, from the Latin acumen, a point. It has an extended termination, and in this respect differs from the lanceolate leaf. The cornus alternifolia and reed are examples. This figure, 25, and the following, 26, show the primary nerves which arise directly from the petiole and midrib. A hastate leaf, Folium hastatum, figure 26, from the Latin hasta, a spear or halberd shaped. Triangular, with lobes projecting perpendicularly to the petiole. The Polygonum hastatum and bittersweet are examples. This leaf is an instance of an angular nerve leaf. A sagittate leaf, Folium sagittatum, figure 27, from the Latin sagitta, an arrow, a leaf resembling the head of an arrow. The lobes at the base are elongated and scarcely diverged from the petiole. Example, Polygonum sagittatum, called tear thumb, and turkey seed. A palmatolobate leaf, Folium palmatolobum, figure 28, from the Latin palma, palm of the hand, having lobes which give it some resemblance to the hand. This figure illustrates a palminerve leaf. Example, the liquid amber styracifera, called sweet gum. A palmate leaf, Folium palmatum, figure 29, hand-shaped, divided nearly to the insertion of the petiole into oblong lobes of similar size, but leaving a space entire like the palm of the hand. Examples, the Viola palmata, the passion flower, and castor plant, also the red and sugar maples. A trilobate leaf, Folium trilobatum, figure 30, from the Latin trace, 3, a leaf formed of 3 lobes, the margins of which are rounded. A lyrate leaf, Folium lyratum, figure 31, from the Latin lyra, a lyre. A leaf supposed to resemble the shape of a lyre. It is cut into several transverse segments, generally larger towards the extremity of the leaf, which is rounded, as in Salvia lyrata, lyre-leaved sage, and garden radish. A sinuate or sinuose leaf, Folium sinuatum, figure 32, a leaf having deep fissures or sinuses, bending in and out. Sinus, the bays or recesses formed by the lobes of leaves or other bodies, are so called. Example, the Argemone mexicana. A doubly serrate leaf, Folium duplicato serratum, figure 33, from the Latin serra, a saw, having teeth like a saw, the larger teeth being notched, also with teeth. See figure 48. Figure 33 shows the secondary nerves arising from the primary. A repand leaf, Folium repandatum, figure 34, from the Latin repandus, bent. A leaf having a margin undulated and unequally dilated is so called. Example, the hydrocotyle. An amplexicol leaf, Folium amplexicol, figure 35, from the Latin amplecto, I embrace, and caulis, stem, stem embracing. A leaf or bract whose base projects on each side so as to clasp the stem with its lobes. Example, Papaver somniferum. A connate or double perfoliate or doubly amplexically leaf, Folium connatum, 36, from the Latin con, together, and natus, grown, joined together at the base. Example, Eupatorium perfoliatum, bone set. A perfoliate leaf, Folium perfoliatum, figure 37, from the Latin per, through, and folium, leaf. A leaf having the stem running through it. The annexed figure, 37, is an illustration of a curvinerve leaf. Example, Alvularia perfoliata, or bellwort. A pandurate leaf, Folium panduratum, figure 38, from the Latin pandus, bent or bowed inward in the middle. Fiddle-shaped. It is also termed panduriform. It is oblong, broad at the two extremities, and contracted in the middle. Example, Convolvulus panduratus, Virginia bindweed, and Convolvulus imperati, native of Egypt, Italy, etc. A runcinate leaf, Folium runcinatum, figure 39, from the Latin runcina, a large saw, to saw timber. Example, Leontodon taraxacum, common dandelion. Dandelion, a corruption of the French dent de lion, lion's tooth. An undulate leaf, Folium undulatum, figure 40, from the Latin undula, a little wave, having the edges irregularly waved. Example, Asclepias obtusifolia. A crenate leaf, Folium crenatum, figure 41, having rounded teeth, which are not directed towards either extremity of the leaf, as in the garden pink, ground ivy, and heartsease. Crenulate, finely crenate. Some leaves are doubly crenate, that is, bicrenate. Example, the Quercus prinus, chestnut oak of Pennsylvania. A lobate leaf, Folium lobatum, figure 42, divided more deeply than toothed or dentate, by somewhat obtuse incisions of an uncertain depth. Each portion is termed a lobe. The number of lobes is sometimes specified. Example, the Liriodendron tulipifera, or tulip tree, also called poplar, canoewood, sugar maple. A reniform leaf, Folium reniform, figure 43, from the Latin ren, kidney, and forma, form, shape, kidney-shaped. A short, broad, round leaf with a sinus or hollow at the base. This figure shows the tertiary nerves springing from the secondary. Example, Acerem canadense, colt's foot. A spatulate leaf, Folium spatulatum, figure 44, from the Latin spatula, a broad slice or knife to spread plasters, oblong or obversely ovate, with lower part much attenuated. Example, the Polygala lutea. A peltate leaf, Folium peltatum, figure 45, from the Latin pelta, a shield, where the petiole is inserted into the middle of the leaf on the underside, like the arm of a man holding a shield. This figure, 45, is also an illustration of a peltinerf leaf. Example, the common nasturtium. A deltoid leaf, Folium deltoides, figure 48, from the Greek letter delta and eidos, resemblance. Example, Populus nigra. A dentate leaf, Folium dentatum, figure 47, from the Latin dens, a tooth. The edge having horizontal, distant teeth. This term, as well as the following, refers only to the edge or margin of the leaf, without regard to its general form. Example, Populus grandidentata. A cerate leaf, Folium serratum, figure 48, from the Latin serra, saw. The edge being cut into notches, like saw teeth, ending in sharp points, which incline towards the apex of the leaf. The nettle, rose, and peach are examples. A rhomboid leaf, Folium rhomboideum, figure 49, rhomb-shaped. A rhomb, in geometry, is a four-sided figure having its opposite sides equal. When the angles are right angles, it becomes a square. An auriculate or eared leaf, Folium auriculatum, figure 50, from the Latin auricula, a little ear. It has two small rounded lobes projecting at the base. The Magnolia auriculata and Rumex acetosella are examples. A cordate leaf, Folium cordatum, figure 51, from the Latin cor, a heart. Heart-shaped, ovate, with two rounded lobes at the base. Example, the Pentadaria cordata and common morning glory. Obcordate is the cordate reversed, the sinus and lobes being at the summit instead of the base of the leaf. See figure 20. An obovate leaf, Folium obovatum, figure 52, from the Latin ovum, egg. The reverse of ovate, egg-shaped, with the base broader than the apex, and the length greater than the breadth. See figure 20. Example, the Arbutus uvi ursi. An elliptical or oval leaf, Folium ellipticum, figure 53, having a regular outline resembling an ellipse. The curves of both ends are alike, and it is longer than it is wide. Example, the Magnolia glauca, common magnolia or beaver tree. An orbiculate leaf, Folium orbiculatum, figure 54, from the Latin orbis, an orb, having a circular outline. Example, the Glycine tomentosa. A cuneate or cuneiform leaf, Folium cuneiform, figure 55, from the Latin cuneus, a wedge, wedge-shaped, broad and obtuse at the summit, and tapering gradually almost to a point at the base. Example, the Quercus nigra, the true black oak or blackjack. A partite leaf, Folium partitum, is one deeply divided nearly to the base, as Helleborus viridis, and according to the number of its divisions, it is bipartite, tripartite, or multipartite. A multipartite leaf, Folium multipartitum, figure 26, from the Latin multus, many, and pars, part, much divided, having deep and very distinct divisions. A laciniate leaf, Folium laciniatum, figure 57, from the Latin lacinia, a lappet, a separate fold of a garment. Divided by deep incisions, the laciniae or parts being quite slender and numerous. Examples, the Dentaria laciniata and the Rudbeckia laciniata. Also, the lower leaves of the Clematis flammula, Sweet Virgin's bower. End of Lesson 3, Part 1. Section 4 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Botany by William Ruschenberger. Lesson 3, Part 2. Examples of compound leaves. Compound leaves may be referred to two classes or divisions, one containing digitate and the other pinnate leaves, accordingly as they are supposed to resemble fingers, digitus, or feathered stems, pinnatus. First, of digitate leaves. A conjugate or binnate leaf, figure 58, conjugate from the Latin conjugatum, which is formed from con, together, and jugum, a yoke, yoked together. Binnate, from the Latin bis, two, and natus, grown. When a common petiole bears two leaflets on its summit. A ternate leaf, Folium ternatum, figure 59, from the Latin ternus, three, and three, when three leaflets arise from one petiole. Example, the Trifolium pratense, red clover. Biternate, twice three-leaved, the petiole divided into three parts, and each part bearing three leaflets. Triternate, three times three-leaved, a common petiole divided into three parts, and each of these parts subdivided into three, and each subdivision bearing three leaflets, as in the windflower. A ternate leaf, which is also doubly serrate, figure 60, that is, Folium ternatum, Folius duplicato serratus, a ternate leaf with doubly serrate leaflets, as in Indian psychic, Spirea trifoliata. A quaternate leaf, Folium quaternatum, figure 61, from the Latin quater, four, having four leaflets growing from a common petiole or leaf stalk. A quinquefoliate or quinnate leaf, Folium quinquefoliatum, figure 62, from the Latin quinque, five, and folium, leaf, having five leaflets growing from one common petiole. Example, ginseng, Panax quinquefolium. Panax is derived from the Greek pan, all, and ekos, a remedy for all things. It is an almost universal medicine among the Tartars and Chinese, and according to them, it is capable of relieving fatigue of both body and mind. It is a native of North America, where it is not esteemed as a medicine. A digitate leaf, Folium digitatum, figure 63, composed of 7 leaflets, an example of which is afforded in the perennial lupin, which is common in the neighborhood of Philadelphia. Digitate, from the Latin digitus, a finger, compared to the spread of fingers of a hand. When several leaflets arise from the very summit of the petiole, as in the horse chestnut tree and high blackberry. The second division of compound leaves called pinnate. A pinnate leaf, folium pinnatum, figure 64, from the Latin pinnatus, winged or feathered, having leaflets arranged along each side of a common petiole, like the feather of a quill. A bipinnate leaf, folium bipinnatum, figure 65, as that of the Mimosa farnesiana, doubly winged, a common petiole bearing pinnate leaves on each one of its sides. Most of the acacia tribe have bipinnate leaves. Bipinnate, from the Latin bis, two, and pinna, wing, two-winged. A bipinnate leaf, folium bipinnatum. We have examples of leaves of this kind in the pride of China, Melia aziderach. Here the leaflets of the secondary petiole are unequally pinnate. See figure 70. A tripinnate leaf, folium tripinnatum, figure 67, from the Latin tres, three, and pinna, wing, conium maculatum, common hemlock, common in many parts of the United States. When the common petiole has bipinnate leaves on each side. A pinnate leaf with bijugate leaves, figure 68, folium pinnatum, foliolus bijugus, from the Latin bis, two, and jugum, yoke, formed of two pairs of leaflets, as seen in the Cassia abscess of India and Egypt. An abruptly pinnate leaf, when the petiole of a winged leaf ends without a leaflet or tendril, as in the American senna, it is abruptly pinnate. When the leaflets of the opposite sides alternate, it is alternately pinnate. And when the leaflets are alternatively large and small, it is interruptedly pinnate. When the leaflets are opposite or in pairs, as in the annexed figure 69, it is oppositely pinnate. An unequally pinnate leaf, folium impari pinnatum, figure 70. Example, the shellbark hickory. When a pinnate or winged leaf is terminated by a single leaflet, as roses, etc., it is equally pinnate, because the pinnae or leaflets are not of an even or equal number. When the leaflets are cut in fine divaricated segments, embracing the footstalk, we have the verticillato pinnate leaf. The lyrato pinnate, in a lyrate manner, having the terminal leaflet largest, and the rest gradually smaller, as they approach the base, like Erisium praecox, and with intermediate, smaller leaflets, Geum rivali, also the common turnip. Such leaves are usually dominated lyrate, in common with those properly so called, whose shape is simple and not formed of separate leaflets. Nor is this from inaccuracy in botanical writers. The reason is that these two kinds of leaves, however distinct in theory, are of all leaves most liable to run into each other, even on the same plant. End quote. Smith. A seroso pinnate leaf, folium seroso pinnatum, figure 71, from the Latin cerus, a tendril, a climber. Example, the tamarind tree, Tamarindus indica. In this form of leaf, a tendril supplies the place of the odd leaflet, as in the pea and vetch tribe, constituting the remarkable difference between it and the unequally pinnate leaf, figure 70. A pedate leaf, folium pedatum, figure 72, from the Latin pes, in the genitive case, pedis, foot. A compound leaf, the divisions of which give it a resemblance to a foot with outspread toes. This is an example of the pedalinnerve leaf, see page 39, in which there is no decided midrib, but the vessels diverge in two strong lateral nerves, from which branches are given off, on that side only which is towards the apex of the leaf. Example, Helleborus fetidus. A pedate leaf with compound leaflets, folium pedatum, folius compositus. Example, the maidenhair, Adiantum pedatum, a very common plant in the neighborhood of Philadelphia. The most singular of all the various leaves are those of the pitcher plants. The pitcher of the Nepenthes, 74, C, is provided with a perfect lid or cover, which is closed in dry weather as if to prevent evaporation, and open when it is rainy or damp. It has been suggested that these pitchers, were designed as reservoirs in which water is stored for the occasional use of the plant in extremely dry weather. When the petiole becomes dilated and hollowed out at its upper end, the lamina being articulated with and closing up its orifice, as in Sarracenia, figure 74a, and Nepenthes, figure 74c, it is called a pitcher or ascidium. If it is enclosed and is a mere sac, as in Urticularia, figure 74b, it is called ampulla. The surface of a leaf may be ribbed or nerved, having fine elevations, running from one extremity to the other without branching, or veined, having prominent divisions near the base, and finer and smaller as they extend over the leaf, as in the mullein, or wrinkled, rugose, rough, or corrugated, like the leaf of the sage, or plicate, plated, having a surface formed into ridges and channels by the alternate rising and sinking of the nerves of the leaf, or smooth, when without wrinkles or ribs, or villose or velvety, when covered by soft down or hairs. Besides the general form, the character of the margin and surface of the leaves, their position, is also described. When upright, and the leaf forms a very acute angle with the stem, it is erect. When they are at right angles with the stems and parallel with the horizon, they are horizontal. When the apex of the leaf hangs lower than the insertion of the petiole, it is reclined. When the base of the leaf is turned in one direction and the apex in another, that is twisted, it is oblique. Radical leaves are those which grow very near to the root. When leaves arise, one after the other, from opposite sides of the stem, they are alternate. But when they arise on the same line, from opposite sides of the stem, they are opposite. When they grow in a circle around a stem, they are verticulate, whorled, or stellate. Exhalation. 30. When treating of absorption, we saw that vascular plants pump up, by their roots, a considerable quantity of water, holding different matters in solution, and that this liquid rises through the stem to reach the leaves. But all the water thus absorbed does not remain in the interior of the plant, and a great part is dissipated in the form of vapor. To satisfy ourselves on this point, it is only necessary to place in a perfectly dry glass jar the leafy stem of a vegetating plant, and expose the whole to the sun. We soon discover little drops, which arrange themselves on the parietes of the jar. By weighing plants immediately after they have been watered, and weighing them again some time afterwards, we obtain proof of this loss, and we may exactly estimate the quantity of water exhaled. It was found by an experiment of this kind that a cabbage lost by evaporation 19 ounces of water a day, and a helianthus, from the Greek helios, the sun, and anthos, flower, or sunflower, loses even a more considerable quantity in form of vapor. 31. A small part of the water thus expelled evaporates through the tissue, which constitutes the surface of all parts of the plant, as well after death as during life. And it is for this reason that the stem, fruit, tubercles, and flowers terminate their existence by drying, when the place in which they may be is not very damp. But the greatest quantity of water is expelled through the leaves of the living plant, and this exhalation only takes place while the plant is alive, and when the influence of light causes the stomata to open. It has been ascertained that the quantity of water thus exhaled is in proportion to the extent of the leafy surface of the plant, and the number of stomata. Thus, fleshy plants, which have but few stomata, lose very little by aqueous exhalation. 32. Light, as we have said, has the property of causing the stomata to open, but these orifices close when the plant is placed in the dark. During the night, plants lose very little by evaporation, and it is known that the best way of preserving a bouquet as fresh as possible is to put it in an obscure place, or at least shelter it from the light of the sun. 33. Exhalation is more active in dry, warm air than when the atmosphere is cold and damp, and it takes place more actively in young leaves than in those of which the surface has been hardened by age. The water that thus escapes is almost pure, and it is estimated that, under ordinary circumstances, it is equal to about 2/3 of the quantity of liquid absorbed by the roots. Sometimes this exhalation becomes even more abundant than absorption, and causes the death of the plant. This often happens when we transplant a tree in spring without taking sufficient care to lop the branches, or by taking it from the earth, we destroy a great many radicals of the root, and absorption is consequently less active. In order to proportion the exhalation to this enfeebled absorption, gardeners leave but a small number of leaves on the summit of the stem. Respiration. 34. Plants cannot live when deprived of air, and are, just as much as animals, under the necessity of constant respiration. But their respiration is carried on in a different manner from that of animals. 35. All parts of the plant, root, stem, and flowers, as well as the leaves, continually absorb a certain amount of oxygen from the air, which combines with the carbonous particles of the sap, and thus forms carbonic acid. But this carbonic acid is not expelled as in animals, but serves for nutrition. Parenthetic remark. Before we proceed further, let us endeavor to obtain clear notions of the meaning of the words oxygen and carbonic acid. The air we breathe, called atmospheric air, is a compound of about 1 part of oxygen gas to 4 parts of nitrogen gas, and a very much smaller proportion of carbonic acid gas, together with some watery vapor. Oxygen and nitrogen are simple substances, that is, chemists have not been able to decompose them. But carbonic acid gas is a compound substance, that is, it consists of more than one material or substance. This name, oxygen, is formed from the Greek oxus, acid, and gynomai, I beget, and was so called because it was believed without it there could be no acid. Although there are acids which contain no oxygen, we know that without its presence, every living thing, animal or plant, would die, and all fire would be extinguished. It is indispensable to respiration and combustion. The word nitrogen was formed from the Greek nitron, niter, and gynomai, I beget, because it was discovered to be one of the essential constituents of niter, and also of nitric acid. It was also called azote from a, privative, and zoe, life, because it would not support animal life. Carbonic acid consists of carbon and oxygen. Carbon, from the Latin carbo, coal, is the name of a simple substance or element. It occurs naturally in the form of the diamond, which is pure carbon, of plumbago or black lead, anthracite, and bituminous coals. It is an elementary constituent of all wood. It seems to be the true food of plants, without which they die. Lamp black and charcoal are forms of impure carbon. The chief action of vegetable organization is to obtain and form carbon. Carbonic acid exists in the atmosphere as the product of combustion, and of the respiration of animals, the frothing of beer, and the sparkling of champagne and mineral water, depending on its presence. 36. The leaves and other green parts of plants also absorb the carbonic acid gas contained in the air, and, by the process of respiration, this fluid, as well as the carbonic acid formed in the interior of the plant, is decomposed. Its carbon remains in the tissue of the plant and nourishes it, while the oxygen is thrown off and mingles with the atmosphere. 37. We now see that the relations of plants with the air are more complicated than those of animals with the same fluid. The latter absorb oxygen and in its place exhale carbonic acid. Plants absorb oxygen and carbonic acid and exhale oxygen, arising either from the quantity of this gas previously absorbed or from the decomposition of the carbonic acid derived from the atmosphere. 38. In general, it is the last phenomenon, that is, the absorption of carbonic acid, its decomposition, and the exhalation of oxygen, that is designated under the name of respiration of plants. Its effect, as we see, is to destroy the carbonic acid, which the respiration of animals is unceasingly diffusing through the air, and consequently to purify the atmosphere. 39. The green parts alone possess the property of decomposing carbonic acid in this way, and they cannot effect this decomposition without the direct influence of the light of the sun. Thus, a plant which is put in an obscure place ceases to respire, languishes, bleaches, and dies after a shorter or longer time. 40. Consequently, the leaves are the principal seat of respiration, and this function is only carried on during the day. 41. It is easy to demonstrate the influence of light upon the respiration of plants. A simple experiment is sufficient to do this. If we place leaves in water containing a small quantity of carbonic acid in solution and expose them to the sun, we see bubbles of air rise from them. But if we place them in the shade, this disengagement of gas is arrested. 42. In leaves exposed to the air, the absorption of carbonic acid takes place chiefly through the stomata, and this fluid acts upon the sap in the interior of the cavities, which exist in the parenchyma of the leaf, and abandons its carbon to pass the state of free oxygen. The intercellular passages, meatus, of the leaves consequently perform, in the respiration of plants, functions analogous to those of the pulmonary cells in terrestrial animals. And it is remarkable that in aquatic plants, the leaves of which are submerged, there are no similar cavities, and respiration is carried on by the surface of the leaves, just in the same manner as the skin or projecting branchiae perform this function in aquatic animals. 43. During the night, the leaves, instead of purifying the air, absorb oxygen, and consequently contribute towards its vitiation. For this reason, as well as on account of the odor they exhale, it is often dangerous to place plants, or even bouquets of flowers, in sleeping apartments. 44. The absorption of oxygen by the parts of plants that are not green is feeble, but it takes place by day as well as by night, and it is necessary to the life of all plants. It is because roots do not obtain the air which they require that they die when too deeply buried, and it is for the same reason that a seed will not germinate when removed from the action of the atmosphere. Of the use and mode of distribution of the nutritive juices. 45. The sap elaborated in the leaves, as we have seen, again descends to other parts of the plant, and constitutes the nutritive juice, by the aid of which its growth is effected. 46. It is easy to be convinced that the nutritive juices of plants are formed in the leaves, for, if we strip a tree of all its leaves, it will cease to grow until it is furnished anew with these organs, and farmers who cultivate mulberries for feeding silkworms have remarked that the growth of the trees is less in proportion to this frequency of stripping them of their leaves. 47. The movement of the nutritive juice, that is, the descending sap, is slow, and always takes place from the leaves toward the roots, whatever may be the position of the branches that this liquid traverses. 48. The route followed by the descending sap is not the same as that by which the sap rises from the roots to the leaves. Instead of traversing the ligneous layers, it descends chiefly through the substance of the bark. 49. The following experiment proves that it is the descending sap which especially serves for the nutrition of the plant, and that this same sap moves in the interior of the bark. If we remove from a branch or the trunk of an exogenous tree a circular strip of bark, we prevent the sap that descends from the leaves to the lower part of the plant from continuing its route. And, in fact, we see that the portion of the stem which is below this annular or ring-like section ceases to grow, while the part situate above profits more than usual, and swells out on the upper margin of the wound so as to form a ring. The same thing happens when we surround a branch by a very tightly drawn cord, for in this way we may also arrest the descending sap, and the parts where this juice accumulates are benefited at the expense of those situated below. 50. For this reason, gardeners sometimes make annular incisions through the whole thickness of the bark around a branch filled with fruit, so as to retain the nutritive juice and augment the size of the fruit. 51. The greater part of the descending sap is found, as we have before stated, in the bark, but it appears that this liquid also traverses the young layers of the alburnum, and it is by its action that we explain the transformation of this alburnum into perfect wood, or duramen. Duramen, Latin, hardening. 52. The descending sap appears to be chiefly composed of water, holding gum, and some other substances in solution. It must be regarded as the chief source from which the plant derives the materials composing, first, the excreted products, second, the peculiar juices secreted in the different organs and designed to remain in the interior of the plant, third, the new tissues. We shall now study these phenomena successively in order. Of secretions, plants, as well as animals, form in certain parts of their bodies peculiar liquids, which differ from the generally diffused juices. And it is to this process, by which these peculiar fluids are formed, as well as to the liquids themselves, that we give the name of secretion. Footnote: secretion, from the Latin secernere, to separate. The process by which organic structure is enabled to separate, from the fluids circulating in it, other different fluids. The function of secretion is usually performed by glands, and each gland secretes a peculiar fluid, according to its structure. For example, the liver secretes bile, that is, it separates from the blood circulating in the liver the materials which it forms into bile. The salivary glands secrete saliva, and the mammary glands in females secrete milk, etc. Now bile, saliva, and milk are also termed secretions. 54. The matters secreted may be thrown out or expelled, or they may be destined to remain in the interior of the plant and subserve the purposes of nutrition or some other function. 55. The matters that plants excrete in this way are very various. A great many plants produce in reservoirs, situate near the external surface, volatile oils that evaporate through the tissue and diffuse themselves through the air. The odor of flowers, and also of certain leaves, depends in a great measure upon this exhalation. It is also to an emanation of this kind that is due a singular phenomenon present in a plant named Fraxinella, which in hot days exhales an essential oil in such abundance that if it be approached with a light, the vapor with which the plant is surrounded takes fire and burns, like that we force out of an orange or lemon skin by pressure into the flame of a candle. Other plants secrete a caustic juice, which is frequently poured out through hollow hairs, and thus produces a lively irritation at the bottom of punctures made by these hairs. The nettle is an example of this kind. Again, we have wax secreted by the leaves or epidermis of young branches, and afterwards expelled. And we have also produced in this way gluey, acid, saline, sugary, and other secretions. 56. These excretions are formed by the roots as well as by the leaves. And as the matters thus expelled are of a nature that is injurious to the plant which produced them, we understand through the knowledge of this fact why plants of the same species do not flourish when kept for a long time in the same soil. For the matters expelled by the roots are deposited in the earth surrounding them, and are again absorbed by the plants growing in it. But the matters expelled by one plant may often be suitable nourishment for a plant of another species, and it is for this reason that the ground often becomes fitted for certain culture when it has been previously made to produce plants in which the excretion by the roots is abundant. The art of assolement, or succession of crops, so important in agriculture, is chiefly based upon the results depending on this excretion by the roots. We give the name of assolement to the succession in the same soil of different crops, combined in such a manner as to produce as largely as possible, and we say triennial, quadrennial assolement, etc., according as the cultivation of the same plant recurs every 3, every 4 years, etc. 57. The liquids secreted by plants and designed to remain in the interior of their organs are designated under the name of proper juices. If they escape externally, it is altogether by accident, and their production appears to be useful to the health of the plant that forms them. These juices are sometimes milky, sometimes resinous, sometimes composed of essential oils, and at other times formed of fatty matters. 58. The milky juices are chiefly found in the bark, and appear to constitute the liquid we see circulating in the vessels of the latex in a great number of plants. The white liquid that runs from the fig tree when it is cut, opium, caoutchouc, India rubber, etc., are juices belonging to this class. 59. The resinous juices are very common in the bark, and are also met with in other parts of the stem. They are formed in little masses which become united together, and descend by their own weight in the tissue of the plant. Sometimes these juices are so abundant that, By making an incision in the tree, we cause a stream to flow out of it, and in this way we collect considerable quantities of its proper juices, as we see in pine and fir trees. 60. The essential or volatile oils are contained in cells or vesicles, and are found in the foliaceous or cortical parts of plants, and the proper juices constituted of fatty oils are chiefly found in the seeds. 61. The solid matter found in the elongated cells of the wood, and on this account called lignin, from the Latin lignum, wood, may also be considered as being the product of a species of secretion, as well as the fecula, which is produced in great abundance in certain parts of plants, seemingly forming deposits of nutritive matter destined at a future time for the nourishment of the plant. This last substance has the appearance of small, white, hard grains, which seem to be composed of different layers, the exterior of which are hardest, and the most internal are similar to gum. It is found isolated in the cells of the cellular tissue, and in some parts of certain plants, such as the seeds of wheat or of rye, the tubers of the potato, the ligneous stems of monocotyledonous plants, etc. It forms considerable masses. Of the growth of plants. 62. The growth of plants depends upon two phenomena. First, the increase of the diameter of stems already formed. Second, the development and elongation of new branches. We will successively examine both. 63. The cellular tissue of plants, while it is still young and receives a sufficient quantity of nutritious juices, gives rise to new cells, which are at first very small, isolated and soft, but which, in proportion as they are developed, enlarge and harden, and become as closely united to each other as to the cellular tissue upon the surface of which they are formed. Those cells which have ceased to grow no longer possess the power of giving rise in this way to new tissue. They become strongly joined to the young cells with which they are in contact, and hence it is that the growth of plants takes place only from the surface of the most recently formed parts. 64. In exogenous plants, the new tissue is thus deposited between the alburnum and the bark, and it first appears in the form of a viscid matter which is called cambium. Those tissues which arise from the alburnum form around the ligneous body or wood of the stem a new layer of alburnum, exterior to all those that have been already deposited, and those which arise from the bark constitute a new cortical layer, within the layers of bark already formed. Each of these layers increases in thickness for a certain time, then ceases to grow, and at the end of a certain period, in its turn, produces a new layer. 65. Perennial exogenous plants in this way form a new layer of wood and of bark every year, and if we cut through the stem of a tree transversely, we may see the number of zones or rings of which it is composed, and thus count the number of years it has lived. 66. The thickness of these layers varies in different plants, and also varies in the same tree, according to its age, the richness of the soil in which it grows, and the abundance of its leaves, etc. Trees grow most rapidly during the first years of their existence, and it is observed that in old trees, the most external ligneous layers are thinnest. When the soil that surrounds the foot of a tree is more favorable to vegetation on one side than on the other, the roots become unequally developed, and on the side where the largest roots are also found the largest branches and the thickest ligneous layers. 67. The new ligneous and cortical layers are not restricted to covering the surface of the plant, but are prolonged beyond it, and, at different points, form lateral expansions which constitute the new branches. These young shoots are, in general, protected in their first growth by peculiar scales, and then constitute what are called buds. They are ordinarily found at the base of the petioles of the leaves, or at the extremity of the branches in ligneous plants, and at the column or neck of the root in perennial herbaceous plants. Sometimes they are not apparent externally, and are concealed even in the substance of the wood. But in most instances, they have the form of a small projecting tubercle, which shows itself in the summer and is known to farmers under the name of eye. During the winter, they enlarge, and in spring, when the sap begins to rise with strength and to carry toward the extremity of the branches the nutritive matters previously deposited in the roots or in the stem, they rapidly develop themselves. Their scales separate, and we see a young branch spring from them, the leaves of which are at first variously plaited and very close together. This new shoot grows more rapidly in proportion to the abundance of the sap, and during a certain time is elongated throughout its length. But after the first year it ceases to grow in this way, and it then forms laterally, and particularly toward its upper part, new layers of vegetable tissue, which contribute to the increase of the length of its extremity, and at the same time to augment the diameter of its base. 68. In endogenous trees, growth takes place very nearly in the same manner. Only the new parts do not form concentric layers, but simply bundles, fasciculi, of fibers variously arranged, and the buds are ordinarily developed at the extremity of the stem and branches. 69. We have said above that the cells of the cellular tissue, when very young, tend to become united or soldered to each other. This is so true that if we lay bare a portion of new tissue of two neighboring trees and bring these parts together and keep them in contact, they become so intimately united that the two soon form a single body and possess one life in common. The art of grafting plants depends upon a knowledge of this fact. Parenthetic remark. Grafting is an operation by which one plant is joined to another in vital union, in such a manner as to form one. The tree upon which grafting is practiced is called the stalk, and the branch or rudiment of a branch that is fitted to it is named the graft. The stalk is ordinarily a wild shrub, and the graft a cultivated variety of the same plant. In order to succeed, the alburnum of the graft must accurately fit, through the greatest part of its extent, that of the stalk, that is, the tree upon which the graft is implanted. Then the junction, or as it were soldering, of the two barks is effected by the assistance of the cambium. One condition necessary to the success of the operation is that the sap of the two plants shall be similar. For example, the plants of the same genus or of the same family are more readily grafted upon each other than those which belong to different families. Grafting is a very useful operation in agriculture. It serves to preserve and multiply varieties which could not be produced by means of seeds. It saves time by procuring a great number of trees, which are with difficulty multiplied by other means, and accelerates by many years the fructification of certain plants. Gardeners employ 5 or 6 different processes to obtain the development of the bud or graft upon the bark of other trees which they use as stalks. Splice or whip grafting consists in paring down in a slanting direction both the graft and stalk and, after applying them neatly to each other, securing them by strands of bast matting, in the same manner as 2 pieces of rod are spliced together to form a whip handle. The part is afterwards covered with tempered clay, or any convenient composition that will exclude the air. Grafting by approach, or in-arching, is a mode of grafting in which, to make sure of success, the graft or scion is not separated from the parent plant until it has become united to the stalk. End of parenthetic remark. 70. Such are the principal phenomena of the life of nutrition in plants, but they are far from taking place with the same intensity at all times, and their duration is extremely variable. 71. In every plant we observe periods of activity, of languor, and even torpor, and then an augmentation of the vegetative functions. In our climate, these periods correspond with the 4 seasons of the year. During winter, the cold and absence of the leaves in most plants almost entirely arrests nutrition. They are then in a state of torpor, comparable to that which hibernating animals experience, and their buds and roots alone continue to grow. But when returning spring imparts to the plant, thus benumbed, a certain amount of heat and moisture. It awakes in a measure, the sap rises with force, the buds develop themselves, the young shoots or scions become elongated, and vegetation displays all its activity. In summer, the leaves are somewhat hardened and become less suited for attracting the sap and exhaling the liquids which reach them from the roots. Consequently, vegetation is less active, and in autumn this change in the leaves being greater gradually brings about their destruction or fall. At this period, it sometimes happens that buds begin to develop themselves and again attract the sap with force, and this ascent of the nutritive juices causes an elongation of the branches and the formation of new leaves, the freshness of which is in beautiful contrast with the yellow tint of the old ones. But the cold soon enfeebles all these phenomena of life and arrests nutrition, even when it does not cause the fall of the leaves, as ordinarily happens. 72. In hot countries, where there is no winter properly speaking, there are nevertheless periods of activity and repose in plants, which correspond to the dry and wet or rainy season. There, the great heat arrests vegetation, as the cold does in our climate, and the life of plants is reanimated in the rainy season. 73. As we have already stated, a great number of plants are annual, that is, they live only through 1 year. Others complete their growth only in the 2nd year, and die on the approach of the 2nd winter, and are termed biennial. Others again continue to live many years, and are for this reason called perennial plants. All herbaceous plants are annual or biennial. Ligneous plants live many years, and the duration of their lives exceeds everything we could imagine. One of the orange trees at Versailles in France appears to be nearly 400 years old, and a tree of the same species, which may still be seen at the convent of St. Sabin in Rhone, was planted there by St. Dominic more than 600 years ago. In Switzerland, there are linden trees which, to judge from their diameter and the manner in which these trees ordinarily grow, ought to be more than 1,000 years old. And there is a chestnut tree at Sancerre, which was known 600 years ago as the Great Chestnut, from which we may conclude that its age is not much less than that of the lindens we have just mentioned. But the tree most celebrated on account of its longevity is, unquestionably, the baobab that flourishes in Senegal. A botanist named Adenson notices one which 3 centuries before had been observed by 2 English travelers, and on excavating the trunk of this tree, there was found an inscription they had written, covered by 300 ligneous layers. From this, they were able to judge how much this gigantic plant had grown in 300 years, and, comparing this with the diameter of the tree, it was estimated that the probable duration of its existence was upwards of 5,000 years. End of Lesson 3, Part 2.
Section 5 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by J.E.D. Klein. The Elements of Botany by William Reichenberger. Lesson 4, Part 1. Generation of Plants. Multiplication of plants by division, formation of adventitious roots, multiplication of plants by grafting, by tubercles, phanerogamous and cryptogamous plants defined. Structure of flowers. Peduncles, pedicel, floral leaf, bract, involucre, spatulae, glume, torus, receptacle, inflorescence, perianth, calyx, corolla, petals, forms of the corolla, nectary, estivation. Essential parts of flowers: stamens, anther, pollen, pistil, carpel, and ovary. of the reproduction of plants. The multiplication of plants takes place in two ways, sometimes by means of special organs designed to produce the germ of the new individual, and sometimes by the simple division of their tissue. The multiplication of plants by division consists in the separation of a part of an individual, which part continues to vegetate and becomes so complete in itself as to constitute, in its turn, a new individual plant. This phenomena depends upon the fact that the different parts of a plant, placed under favorable circumstances, have a tendency to produce those organs which are wanting to constitute a complete plant, and that the portion which gives rise to these complementary parts becomes fit to live without the assistance of the individual from which it was taken. For example, a branch placed in favorable circumstances may put forth roots, which are called adventitious when they arise in this way, so that, if it be separated from its stem, it will still continue to be nourished, and will constitute a new individual. The same is true of roots. They also have the faculty of giving rise to stems and to leaves, and the root from which a stem and leaves arise possesses all the organs necessary for vegetation, and consequently may continue to live after it has been separated from the plant of which it at first formed a part. Gardeners give the name of shoots or slips to those branches from which they cause adventitious roots to spring, and which they then separate from the parent plant. In general, we succeed in producing these roots by placing in a properly moist situation a branch in which the progress of the descending sap is slow, therefore permitting an accumulation of nutritive matter in it. To arrest in this way the descending sap at a point from which we wish to produce adventitious roots, we sometimes make a circular incision through the thickness of the bark, and place it in a tightly drawn ligature, and then surround it with moist earth. Sometimes we simply bend a branch into the ground because, at the point where it is bent, the nutritive juices, being forced to overcome their own weight in order to ascend toward the stem, are retarded in their progress, and at other times we take advantage of natural knots that exist in a branch and favor the development of adventitious roots. And there are some plants, the branches of which, when surrounded by moist earth or moss, put forth roots without a stagnation of the nutritious juices being necessary. When the roots appear, we cut the branch so as to separate it from the plant to which it belonged, and then it constitutes a new individual. But we do not separate the slip or branch until the roots are formed, that is, when it possesses all the parts that compose a complete plant. But it often happens that a branch cut before it has put forth adventitious roots continues to vegetate and produce roots so as to constitute a new individual. For example, a branch of willow freshly cut and planted in the moist earth promptly takes root and becomes a tree similar to that from which it was detached. It is then called a slip or a sucker. All plants may be multiplied in this way, but with more or less facility. As this operation rarely succeeds, gardeners seldom have recourse to it. It is not the branches alone that may give rise to adventitious roots and constitute a slip or shoot. Sometimes the leaves will perform this office. For example, the leaves of the orange, of the fig, and so forth. Detached from their stems and fixed in the earth by their petiole, will take root by their principal nerve, and afterwards give rise, from the superior surface of their parenchyma, to ascending stems. The multiplication of plants by grafting, of which we have already spoken, is also a mode of propagation that belongs to this class of phenomena, because it is effected by simple division. Only the part of the plant which is separated, instead of becoming complete in itself, forms an intimate union with another plant, and lives at the expense of its roots as a sort of parasite. Propagation by tubercles is another mode of multiplication by division, which is effected by means of buds surrounded by a deposit of nutritive matter, which, being placed in favorable circumstances in regard to moisture, heat, and so forth, may vegetate and put forth a stem and roots. These deposits of nutritive matter are sometimes formed in the roots, sometimes in subterraneous stems, sometimes in the axil of the leaves, ordinarily designated under the name of tubercles, offsets, which, when they have attained a certain size, are usually detached. The potato presents us with a remarkable example of this mode of multiplication. This plant produces along its stems tubercles which are not developed ordinarily except in its subterraneous part, and are only held by a thin thread, so as to be easily separated at the end of the year, either by the slightest force or from the death of the stem from which they grow. Now, each one of these tubercles has upon it several buds or germs, called eyes, enveloped by a mass of cellular tissue containing fecula, etc. If placed in a situation that is sufficiently moist and warm, these buds soon begin to sprout and attract the nutritive matters deposited around them. By means of this nourishment, the buds elongates, the stem and leaves begin to develop themselves, and as soon as they begin to perform their ordinary functions, the nutritive juices prepared within them descend and cause the formation of roots, so as to give rise to a new and complete plant. To recapitulate, we see then that under certain favorable circumstances, all plants may be multiplied by division, and that this division may be effected by shoots, by slips, by grafting, and by tubercles. But in most cases, the reproduction of plants is effected in a manner altogether different, by the means of seeds, which are themselves the production of particular organs, namely flowers and fruits. The special organs destined to secure the multiplication of plants are the flowers, fruits, and seeds. Plants that are provided with perfectly distinct flowers are designated under the name of phanerogamous, from the Greek phaneros, evident, and gamos, married, and those which have no distinct special organs of multiplication are called cryptogamous, from the Greek kryptos, concealed, and gamos, marriage. The flower consists of the assemblage of organs upon which spring the germs of phanerogamous plants and the parts which immediately surround them. Its use is to secure the production of these germs and their fecundation, fertilization, that is, to endow them with the faculty of living and of developing themselves so as to be able to become plants, similar to those from which they were derived. The fruit is the assemblage of these germs already fecundated and of organs destined to protect them until they attain maturity, that is, the state of perfect seeds. And the seed is the germ furnished with various envelopes, that is, the body which by its development becomes the new plant, and the organs designed to protect it or to furnish the young plant its first nourishment. Of the structure of flowers. The flowers, as we have stated above, are the parts in which the germ of the new plant is produced and acquires the property of living and of developing itself. They are composed of appendages analogous to leaves, but of various forms, which arise from the extremity of the stem or its ramifications. Sometimes the flowers arise immediately from the stem without being attached to it by a tail or any accessory part. In this case, they are termed sessile, from the Latin sessilis, dwarfish, that is, without a stalk or stem. But in general, that portion of the stem which bears them is prolonged and constitutes a sort of tail, analogous to the petiole of a leaf. To this support we give the name of peduncle, from the Latin pes, a foot, a little foot. When it is divided, each one of the divisions that is terminated by a flower is called a pedicel. For example, pedunculate flowers have the talar stem simple, as in the common pink, and pedicellate flowers have several tails springing from one common to the whole, as in bunches or clusters of lilac, of the vine, and so forth. The peduncle or the pedicel of a flower may arise from the very extremity of the branch that bears it, or laterally, and in this last case it arises from the axil of a leaf, which on this account has been called floral leaf, when it resembles other leaves, and is named bract, from the Latin bractea, a thin leaf of metal. When it differs from the other leaves in its color, its form, or in the absence alone of the buds in its axil. These bracts may be found at the base of the peduncle, or at the base of each of its divisions, when this support is ramified as in pedicellate flowers. When they are symmetrically arranged around one or several flowers, so as to form a kind of accessory envelope, the assemblage is called an involucre, from the Latin involutus, folded in. Generally, they have a foliaceous consistence, but they sometimes resemble little scales, more or less closely embracing the base of the flower. When the involucre surrounds a single flower and is very close to it, it often resembles one of the proper envelopes of the flower, called calyx, Latin, the cup of a flower, and in this case it is commonly known under the name of calycula, as in the mallow. When the involucre entirely covers a flower before it is blown, and the flower is not seen externally until this envelope is torn open or unrolled, it is called a spathe, from the Greek spathe, a ladle. The common onion, narcissus, the palm, etc. are examples. Finally, the bracts of some plants are in the form of two small scales, which seem to be in the place of the proper envelopes of the flower, and then they constitute what botanists call glume, from the Latin gluma, a husk of corn. The terminal portion of the pedicel, which gives rise to the different parts of the flower, is called torus, from the Latin torus, a bed. When the terminal extremity of a peduncle is divided into a great number of pedicels, and these are very short, we generally remark that the principal support is widened and thickened, and to this dilated portion of the peduncle we give the name of receptacle. It contains a deposit of nutritive matter destined to assist in the development of the flowers situate above, and it is sometimes entirely fleshy, as in the artichoke. Sometimes it is so concave as to completely enclose the flowers and fruits that arise from it, as is seen in the fig tree. We give the name of inflorescence to the arrangement which the flowers assume on the stem, and we give special names to the different arrangements they assume. For instance, those flowers which spring from the axil of an ordinary leaf are called axillary flowers, and these axillary flowers are again distinguished by the term solitary, geminal, ternary, quaternary, and fascicular, according as 1, 2, 3, 4, or a greater number spring from the axil of the same leaf. And we give the name of verticulate to flowers which arise from the axil of leaves which are also verticulate, and form a kind of ring around the stem. Terminal flowers are those found at the extremity of the stem or a principal branch, and accompanied at their base by two opposite bracts. The term spike is applied to axillary flowers which are arranged upon a common but simple and not ramified axis, as in the wheat, etc. When unisexual flowers furnished with scales, the known pedicle of which is similar to that of the spike, but is articulated at its base in such a manner as to be entirely detached after inflorescence, as, for example, in the flowers of the willow, elm, beech, oak, etc. It is called a catkin. When all the flowers are borne upon a common peduncle, irregularly branched, they are termed a cluster, as in the horse chestnut. When flowers are arranged on the stem similarly to a cluster, but have the secondary divisions very much elongated and widely separated from each other, they form a panicle, as in the male flowers of the maize or Indian corn. Diceras is a sort of cluster, the axis of which is much elongated, and the branches of which, in particular, have the same arrangement as the assemblage of the cluster, as in the lilac and vine. A corymb is where all the flowers, the pedicles of which with their ramifications arise from the upper part of the stem at different points, and reach to nearly the same height as in the milfoil. When the pedicles are of equal lengths and arise from the same point, diverging and ramifying in a uniform manner, so that the assemblage of flowers presents an arched surface like the top of an extended parasol, we have an umbel, as in the carrot, parsley, hemlock, etc. We give the name of capital to an assemblage of a considerable number of little flowers upon a common receptacle that is wider than the summit of the pedicle and surrounded by a particular involucre, as in the artichoke, milk thistle, the marigold, the sunflower, etc. Capitals are often designated under the name of compound or composite flowers, because at first sight the assemblage of all the flowers borne upon a common peduncle appear to form only one and the same flower. The flower itself is ordinarily composed of two series of organs, namely the essential parts, which occupy the center, and the accessory or tegumentary parts, which occupy the circumference and serve to protect the first. These tegumentary parts of the flower constitute what is called the perianth, from the Greek peri, around, and anthos, flower. Sometimes they are wanting entirely, and at other times they are imperfect, but in most instances they form around the essential organs of inflorescence two envelopes, the most external of which is called the calyx, cup of the flower, and the second, which is situate above and within the preceding, is named the corolla, from the Latin corolla, a little crown. Calyx. The calyx, or the external envelope of the flower, is composed of a variable number of appendages, analogous to leaves, which are called sepals. They are arranged nearly in a circle around the inferior part of the flower. Their color is generally green, their surface is furnished with stomata, and their structure is similar to that of leaves. Sometimes all the sepals are perfectly distinct and may be separated without breaking their tissue. In this case, they constitute a polysepalous calyx. At other times they are joined, or as it were, glued together, in such a way that the calyx appears to be formed of a single piece, and is then designated under the name of monosepalous or gamosepalous calyx. When this junction extends throughout the whole extent of the sepalous, the calyx is entire, but in general it occurs only at the base, and then the terminal and free portion of the sepals constitutes the lobes or teeth, which occupy the upper part of the calyx and spread more or less. We give the name of tube to the lower and commonly contracted part of a calyx thus formed, and the superior and open part is called the limb. In most dicotyledonous plants, the calyx is composed of 5 sepals, and when these appendages are united at the base, presents 5 lobes. Sometimes, however, there are only 3 or even 2, and there are examples of a greater number. Its form varies. Sometimes it is regular, that is, composed of parts entirely like each other, sometimes irregular, that is, consisting of parts that differ from each other in form or size. Sometimes certain sepals are united to each other for a shorter distance than the rest, so as to form divisions of an equal size, and constitute what botanists term a labiate calyx, labiate from the Latin labium, lip. The sepals, like the leaves, are sometimes caudicous, from the Latin caudo, I fall, and sometimes persistent, from the Latin per, through, and sisto, I remain. After inflorescence, they sometimes dry where they are, and at other times, on the contrary, they enlarge and become fleshy. Their form varies. Some are lanceolate, lance-shaped, or pointed. Others are blunt, and others again are cordiform, heart-shaped. In some plants their extremity is hardened so as to resemble a spine or a long hair. The whole of the calyx formed by the assemblage of the sepals also presents considerable differences. The monosepalous calyces may be tubular, or elongated in the form of a tube, as in the pink. Urosylate, from the Latin urisus, a pitcher, or in form of a pitcher or urn, contracted above the limb and then dilated, as in the rose. Campanulate, from the Latin campanula, a little bell, or in form of a bell. Vesicular, compressed, angular, etc. The polysepalous calyces also vary. Some are tubular, others are campanulate, others stellate, star-shaped, etc. Corolla. The internal envelope of the flower, or corolla, is composed, like the calyx, by the union of a certain number of lamellar appendages somewhat analogous to leaves, which are arranged circularly in one or more rows or whorls. To these appendages we give the name petals, from the Greek petalon, a leaf, and it is to be observed that they differ from leaves more than the sepals. They have but few stomata. Their nerves, which are similar to those of the leaves as regards their direction, are more slender, and contain no other kind of vessels but trachea. They are very seldom green, but generally possess the most brilliant colors. The corolla is sometimes monopetalous or gamopetalous, that is, composed of a single piece, formed by the intimate union of all the petals, as in the flower of the bindweed. At other times it is polypetalous, that is, composed of a greater or less number of separate petals, as in the rose, pink, etc. The number of petals is ordinarily 5, in which case they are arranged around the essential organs of the flower in a single row or whorl or verticulus. Sometimes there are 3 or 4 only, or 7, and at other times a much larger number, and then they are placed so as to form several concentric whorls, verticelli, and to alternate with those of the neighboring row. Polypetalous flowers are called dipetalous when they have 2 petals only, tripetalous when they have 3, tetrapetalous, pentapetalous, hexapetalous when they have 4, 5, and 6 petals, and so on. We generally recognize in a petal the claw, or inferior part, corresponding to the petiole of the leaf, which is more or less contracted, and the limb, which is more or less spread and constitute the upper part. Its form varies much. Sometimes it is rounded, sometimes acute, sometimes hollow, and at other times its base is prolonged like a spur. Like the calyx, the corolla is sometimes regular, sometimes irregular. Sometimes it is caducous, that is, it falls as soon as it is expanded or blown, and at other times it fades in the flower before it is detached, and is then said to be marcescent, and we generally distinguish an inferior, straight portion, which in monopetalous flowers constitutes the tube, a superior part which is more or less flaring, called limb, and a circular line which separates the latter from the tube, and bears the name of throat. The general form of the corolla varies much. The following are its principal modifications. End of section 5.
Section 6 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Elements of Botany by William Ruschenberger. Lesson 4, Part 2, Varieties of the Corolla. Corollas are monopetalous when they are formed of a single petal, and polypetalous when they consist of several petals. Monopetalous corollas are either regular or irregular. The principal forms of regular monopetalous corollas are the following: tubular, when the tube is long, as in the lily. Campanulate, or bell-shaped, example, the campanula. Infundibular, or funnel-shaped, as in the flower of the tobacco. Infundibular, from the Latin infundibulum, a funnel. Cyathiform, or cup-shaped. Cyathiform, from the Latin cyathus, a drinking cup. It differs from the infundibular corolla in having its tube and of course its border less spreading, and from the campanulate in not having its tube appear as if scooped out at the base. Hypocrateriform or salver shaped, when the tube is long and expanded into a flat limb at the throat or entrance into the corolla, as in the primrose. Hypocrateriform, from the Greek upo, under, crater, cup, and forme, shape, salver shaped. The form of a corolla consisting of a tube suddenly expanded into a flat border. Rotate, or wheel shaped, when the tube is very short and the limb expanded and almost flat. Urceolate, or pitcher shaped, when it is dilated towards the base and contracted towards the orifice, as in several heaths, etc. Scutellate, or porringer shaped, when it is expanded and slightly concave, like a basin. The following are the principal forms of irregular monopetalous corollas. Bilabiate, when it is more or less elongated, dilated, and open towards the top, and terminated by two lips, one superior and the other inferior. Personate, or in the form of a mask, when the tube is elongated and the throat dilated and closed above the approximation of the limb, which consists of two unequal lips. Anomalous, when its form is so irregular that it cannot be referred to any of the ordinary types. The following are the principal forms of regular polypetalous corollas. Cruciform, from the Latin crus, a cross, when it is composed of four petals with an elongated claw, arranged in the form of a cross, as in cresses. The four petals have the form of a St. Andrew's cross. The lower part is the unguis, or claw, and the upper part is the to lamen, or border, each petal having the form of a battledore. The claw is somewhat longer than the border. Rosaceous, when the petals from 3 to 5 or more have a very short claw and are expanded as in the simple rose. Caryophyllaceous, from the Latin caryophyllus, the garden pink, when the petals, 5 in number, have very long claws, concealed by the calyx, as in the pink. The following are the principal forms of the irregular polypetalous corollas. Papilionaceous, from the Latin papillo, a butterfly, when the petals, 5 in number, have each a peculiar form, the two lower ones ordinarily united to each other, forming what is called the carina or keel. The two lateral ones are generally expanded and called wings, and the superior one ordinarily erect, various in form, and covered by the other four previous to the blowing of the flower, and called the banner or standard or vexillium, as in the pea, acacia, etc. Anomalous, when petals are irregular without having the papilloneous form, as in the violet. Nectary. The word nectary, from nectar, the food of the gods, is of very general application, and is used to express some peculiar modifications in the sepals or petals, by which they assume an unusual form, but more especially when there is some alteration of the structure by which they are wholly or partially converted into secreting organs, and exude a saccharine glutinous juice. Aestivation. As a condition of the leaf whilst yet in bud is termed its vernation, so the manner in which several parts of the flower lie folded in the flower bud is termed their aestivation. Certain flowers, the tulip for example, instead of having a double perianth, have only a single envelope, and we are not certain whether it is a calyx or corolla. In general, it seems to bear a close resemblance in structure to the calyx, but it sometimes presents the bright colors of the corollas. It is sometimes analogous to the first of these floral envelopes, and sometimes analogous to the second, and at other times again it is entirely formed by the union of the two, which have become perfectly alike. Be it as it may, we give the name of perigonium from the Greek peri, around, and genomai, I grow, to the single envelope, which in other respects may be double or simple, and flowers that possess this mode of organization are termed monoclamidious, from the Greek monos, one, klemos, cloak, and idios, resemblance, apparently having but one covering or envelope. Essential parts of flowers. The essential parts of a flower occupy its center, as has been stated above, and although they are the most important, they are very far from being the most apparent to the eye. These organs are of two kinds. One kind is destined to produce the ovules, or germs, and the other to cause their fecundation. The first bears the name of pistil, and the second is called stamen. Most flowers are provided both with a pistil and with stamens, and consequently possess all the organs necessary for the production and fecundation of germs. They are distinguished by the name of hermaphrodite flowers. Others, on the contrary, possess only stamens or a pistil alone, and are named unisexual. The plants that bear these incomplete flowers are termed monoecious, from the Greek monos, single, oikos, a house. When the two kinds of flowers, those with pistils and those with stamens, are developed on the same plant, but when these different flowers grow on separate plants, some producing flowers with stamens, others bearing flowers with pistils only, they are named dioecious, from the Greek dis, two, and oikos, house. Those which have flowers provided with all the organs are named polygamous plants. Stamens. The stamens are situate between the corolla and the pistil. They are generally in form of filaments, threads, and in no manner resemble the leaves in their youth. Nevertheless, they may be considered as analogous to leaves, because under certain circumstances they are changed into petals. In double flowers, for example, it is by the stamens being changed into petals that the corolla, in place of being simple as in the natural or uncultivated state, presents a greater or less number of whorls. The number of stamens varies much in different plants. Certain flowers, which are on this account named monandrous, from the Greek monos, single, and aner, stamen, have but one stamen. Other flowers, called diandrous, triandrous, tetraandrous, pentandrous, etc., have 2, 3, 4, 5, or more stamens. In general, their number is equal to that of the petals, or is a multiple of the petals. Sometimes they are all alike, and at other times they are not of the same size. When the same flower always has 2 short and 2 long stamens, it is named didynamous, from the Greek dis, twice, and dunamis, power. When the whole number of stamens is 6, and 4 of them are longer than the other 2, the plant is termed tetradynamous, from the Greek teteros, 4, and duonamus, power. These organs form one or more whorls, or verticils, situate within the corolla, and in general those which form the external whorl, or the only verticil, when there is but one, regularly alternate with the petals, so that each stamen corresponds with one of the divisions of the corolla. Each stamen consists of 3 parts, namely, the filament, the anther, and the pollen. The filament of a stamen is a support analogous to the petiole of the leaves and the claw of the petals, and is generally cylindrical and slender. Sometimes it is so short that it seems to be wanting, and in this case the stamen is said to be sessile. Generally, however, it is very long. The filaments arise from the torus or receptacle, that is, from the superior extremity of the pedicel of the flower, between the corolla and the pistil. Generally they are distinct from each other, and entirely free, but sometimes they are joined together, and in this way form one or more bodies, to which we give the name of androphore, from the Greek andros, the genitive of aner, man, anther, and phora, I support, anther bearer. In certain plants, such as the mallows, this cohesion takes place between the filaments of all the stamens, so that the androphore constitutes a tube of greater or less length, in the interior of which the pistil is lodged. At other times the stamens are united in 2 or more bundles, fasciculi, and then form 2 or more androphores. And there are flowers in which the anthers cohere to each other, although the filaments are distinct. The point where the stamens cease to adhere to the neighboring parts varies. Sometimes they arise below the portion of the pistil called the ovary. They are then termed hypogynous, from the Greek upo, under, and guine, woman or pistil. At other times these organs, as well as the petals, seem to arise at a greater or less distance above the calyx, and are then termed perigynous, from the Greek peri, around, and guine, pistil. At other times, again, the portion of the pedicel which bears them is prolonged in the same way between the calyx and the ovary, but adheres to the latter organ as well as to the calyx, and in this instance the stamens seem to rise above the ovary, and are named epigynous, from the Greek epi, upon, and guine, woman or pistil. In consequence of these differences, the stamens may have 4 different and fixed positions. First, upon the internal parietes of the tube of the corolla, when it is monopetalous as in the lilac. Second, upon the ovary, which takes place when the corolla is epipetalous as in the umbelliferous plants. Third, beneath the ovary, which happens when the corolla is hypopetalous, as in the poppy, the cruciferae, the vinae, etc. Fourth, upon the calyx, which always occurs when the calyx bears the petals, as in the rose. The corolla always has the same position as the stamens in all monopetalous corollas. The stamens are attached to the corolla, and in all polypetalous flowers, the stamens are not attached to the corolla. Anther. The anther is the most essential part of the stamen and occupies its summit. Its color is almost always yellow, and it may be compared to the limb of a very small leaf that has become thickened, narrow, and folded upon itself. In its interior the pollen is formed, and it ordinarily consists of two small membranous sacs, named cells or lodges, which are joined together back to back, or by a portion of the superior extremity of the filament, called the connective. Sometimes there is but one of these cells, which seems to be owing to the abortion of one of these pouches, or to the bifurcation of the filament, and at other times there are four. There are some also that are divided internally by partitions. The form and mode of insertion of the anthers vary. Sometimes these organs are elongated, at other times rounded, cordiform, etc. Sometimes they adhere to the filament for a great part of their length, at other times they are attached by one of their extremities only, and at other times again they are fixed at their middle upon the very extremity of the filament. Pollen. The pollen is a yellow dust that is enclosed in the cells of the anther, which by falling upon the pistil causes the development of germs and the formation of seeds. It is composed of extremely small grains, the surface of which is sometimes smooth, sometimes covered by asperities, and their interior is filled with extremely fine dust. The envelope of these grains of pollen is composed of two membranes, and when they come to be moistened, the internal vesicle swells, tears the external membrane, and escapes, forming species of tubes of greater or less length. Pistil. The pistil, or organ that produces the germ, occupies the center of the flower, and is surrounded by the stamens, by the perianth. The portion of the torus, or extremity of the pedicel, where it springs sometimes, takes its rise from the origin of other parts of the flower, so as to form for this organ a special support, named a gymnophore, from the Greek gumnos, naked, and phorio, I support. The pistil is composed of appendages, named carpels, which are somewhat analogous to leaves, but they are folded inwards, and bear on their edges the ovules, destined to become the seeds. In each carpel we distinguish three parts: the ovary, the style, and the stigma. The ovary occupies the lower part, and encloses a cavity or cell, in which the germs are developed. The style is a superior prolongation of the ovary, which is, however, much less, and is often even as slender as a thread. It varies extremely in length. And the stigma is the terminal portion of the pistil which surmounts the style, or, when this latter organ is wanting, it rests on the ovary, and is generally composed of a soft and to the appearance glandular tissue. The number of carpels varies much. Sometimes there is only one, sometimes two or three, or even more, and as we have seen in the case of sepals and petals, these organs cohere more or less completely to each other. When the carpels remain entirely separate from each other, they constitute several distinct pistils, and when they are united into one mass, they form what is ordinarily called a single pistil. Sometimes this coherence takes place through the whole length of the carpels, sometimes in the ovaries, without the styles participating, so that the single mass formed by the ovaries, and ordinarily called a single ovary, is surmounted by two or more styles, and when the styles are united, the stigmas of the different carpels may be separate, or they may cohere. The number of cells we find in an ovary when we cut through the lower part of the pistil depends upon the number of carpels that are united together. Sometimes there is but one, at other times 2, 3, 4, 5, or even more. Its general form is commonly ovid, egg-shaped. Finally, the cell of each carpel encloses one or more ovules, which by being developed become seeds. The relations of the ovary with other parts of the flower vary, and furnish important characters for the classification of plants. Sometimes the base of this organ corresponds to the point at which both the stamens and perianth are inserted, so that the ovary is free at the bottom of the flower. It is then termed a superovary. At other times it is united entirely around the tube of the perianth, so as to form one body with the calyx, and is only free at its upper part. In this case the stamens and petals seem to rise above the ovary, and it is said to be infra, below, or adherent. This latter arrangement carries with it the coherence of the sepals to each other. Therefore, whenever the ovary is infra, the calyx is necessarily monosepalous. End of section 6.
Section 7 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Guero. The Elements of Botany by William Ruschenberger. Lesson 5. Development and Functions of Flowers. Flora's Calendar. Flora's Clock. Fertilization of Flowers. Fruit. Epicarp. Mesocarp. Endocarp. Carpels. Classification of fruits. Seeds, their structure. Embryo. Cotyledons. Germination. Of the development and function of flowers. Flowers are formed in certain plants long before they appear externally. In the palms, for example, they remain concealed a year or even several years before they show themselves. They first appear in the form of a bud, which is generally a little larger than the buds of the leaves, and for a certain time their different constituent parts remain contracted. They are then designated under the name of flower bud. Finally, when they approach a little nearer to the term of their growth, they expand or blow, and it is to this phenomenon that we ordinarily apply the name of inflorescence or flowering of plants. Plants do not fade till they attain a certain age, which varies according to the species and according to circumstances, but this period is deferred in proportion to the slowness of the growth of the plant and the time it is destined to live. For instance, herbs fade on the first year of their existence. Some do not fade until the second year. Most shrubs only die in the second, third, or even fourth year, and in trees this phenomenon is more tardy. A certain degree of heat is necessary to effect inflorescence, and it is remarked that the same plant begins to fade sooner in warm countries than in cold. It sometimes even happens in the latter that certain plants, if they can live at all, never fade. Too much moisture and superabundant nourishment, by favoring the development of the leaves and stem, often contribute to retard inflorescence. When a perennial plant has begun to blossom, it ordinarily produces new flowers every year at about the same period. Sometimes, however, this periodical return of inflorescence does not occur with the same regularity, and when vegetation is injured by any circumstance, it may have barren years. It has also been observed that when a tree has borne a great deal of fruit one year and retained it late, inflorescence is feeble or entirely wanting the succeeding year. And thus it is in the south of Europe, when the olives are left late upon the trees, the harvest fails the following year. Sometimes, on the contrary, the periods of inflorescence are more approximated, and in warm and humid autumns we occasionally see plants flowering a second time. The period of the year at which inflorescence takes place is generally definite for each species of plant, but varies a little according to the temperature and other atmospheric circumstances. For example, in the climate of Paris, which is similar to that of the Middle States, the black hellebore flowers in January, the hazel tree and willow in February, the box, the yew, the almond, the peach, the apricot, the primrose, the stock gillyflower in March, the plum, the pine, the ash, the elm, the yoke elm, the hyacinth, the dandelion, etc., in April, the apple, the horse chestnut, the lilac, the cherry, the peony, in May, the linden tree, the vine, oats, wheat, the wild red poppy, larkspur in June, the violet, the carrot, hemp, lettuce in July, asters, garden balsams, and water hyssop in August, ivy, saffron in September, Jerusalem artichoke, and certain other plants in October. The table of the different epochs of inflorescence constitutes what botanists have named Flora's calendar. In colder countries, inflorescence is retarded, while in the south it occurs earlier. For example, in Smyrna, the almond flowers in the first fortnight of February, in Germany, in the second half of April, and in Christiania, Sweden, in the first days of June. The expansion or blooming of the flower is almost always effected by the separation of the pieces of the corolla and calyx from above downwards, but there are some in which the floral integuments remain adherent to the summit, and separate at the base, as in the vine, for example. The period of the day at which this phenomenon occurs varies in the greatest number of plants, but in some it is fixed, and a series of plants, arranged according to the hour at which the flowers blow, constitutes what Linnaeus called Flora's clock. For example, at Paris, the bearbind, a species of bindweed, blows between 3 and 4 o'clock in the morning. Between 4 and 5, certain of the Chicoraceae expand. Between 5 and 6, the convolvulus tricolor appears. About 7, the lettuces, water lilies, etc. About 8 o'clock, a species of chickweed. About 9, the umbel-flowered marigold. At 10, the ice plant. Towards 11, the purslane and the star of Bethlehem. About noon, most of the ficoids, fig marigolds. About sunset, the evening primrose. Between 6 and 7 in the evening, the marvel of Peru. Between 7 and 8, the privet. And about 10 in the evening, a bindweed, which gardeners call a morning glory, because they always find it open when they rise in the morning. When the flower has arrived at a certain period of its development, the pollen formed by the anthers falls upon the stigma, and in this way causes the fecundation of the ovules enclosed in the inferior part of the pistil. Frequently the stamens are inclined towards the pistil, that they may more conveniently deposit the pollen. For example, in the geraniums, the filaments of the stamens are curved so that the anther rests upon the stigma, and in the nasturtium, the 8 stamens are each inclined in turn for 8 successive days to deposit the pollen on the pistil in this way. And at other times this species of dust is cast into the air, and borne by the wind to the pistil of the same or of a neighboring flower. It is easy to prove that the action of the pollen upon the pistil is indispensable to the fecundation of the ovules and the production of seeds which are developed in this organ. For example, it is sufficient to cut off the stamens of an hermaphrodite flower to render it sterile, provided it be sufficiently removed from other flowers in which the stamens have not been destroyed. And when we have mutilated a flower in this way, it is sufficient to cast upon its stigma some pollen taken from another flower of the same species to make it produce seeds. In monoecious plants, that is, having flowers with stamens and flowers with a pistil only on the same stalk, as the maize, it is only necessary to remove the flowers with stamens to prevent the others from producing seeds. And when the plants are dioecious, that is, when the stamens and pistils are borne on different stems, the fecundating action of the pollen is still more evident. It has been long known that female date trees do not produce fruit, if they are very distant from trees of the same species bearing flowers with stamens, and in this case they will not bear, if we are not careful to dust over the branches at the time of inflorescence with pollen derived from the male date. This operation is daily practiced on date trees in the East, and during the expedition of the French army in Egypt, the war having prevented the inhabitants of that country from procuring, as usual, flowers with stamens, they were deprived of their harvest of dates. The grains of pollen that are deposited on the stigma meet there with moisture, swell, burst, and permit the escape of the granules contained within. These granules penetrate the spongy tissue of the pistil and descend to the ovules which they are destined to fecundate. If the pollen is moistened before it reaches the stigma, it bursts in the same way, but in that case the granules it contains are lost, and fecundation does not take place. For this reason, nature ordinarily gives to the corolla a form or position that protects the stamens against the action of moisture. When the ovules are fecundated, the flower fades, and all the parts situate above the ovary, or that are not adherent to this organ, as is sometimes the case with the calyx, fall or dry up. But the ovules, as well as the parietes of the ovary, rapidly enlarge and constitute the fruit. Of fruit. We give the name of fruit to the fecundated and increased ovary, and by extension we also understand by this term the floral envelopes which may remain adherent to this organ. The fruit is essentially composed of two parts, namely, the ovules or seeds, and the carpels or ovaries which surround them, and for this reason they are called by some botanists the pericarp, from the Greek peri, around, and karpos, fruit. These two parts are never wanting, but the pericarp is sometimes so thin and so closely united to the seeds that without a very careful examination we would not believe that it existed at all. A carpel may be compared, as we have said before, to a leaf folded upon itself, that is, the edges rolled inwards towards its midrib, and like it is composed of three layers, namely an external membrane, which represents the epidermis of the inferior surface of the leaf, and in the fruit is named epicarp, from the Greek epi, upon, and karpos, fruit. A middle layer, which is analogous to the parenchyma of the leaf, and is called the mesocarp, from the Greek mesos, the middle, and karpos, fruit, or sarcocarp, from the Greek sarx, flesh, and karpos, fruit, flesh of the fruit. Finally, an internal membrane, or endocarp, from the Greek endon, within, and karpos, fruit, which corresponds to the superior surface of the leaf. Also, the pericarp, which is nothing but the united or agglutinated carpels, is essentially composed of three layers, namely the epicarp, which occupies the surface of it, the mesocarp, which is more deeply situated, and the endocarp, which lines the lodges or cells in which the seeds are found. The epicarp frequently has upon its surface hairs, glands, and stomata. In general, it is thin and flexible, and is often easily detached from the subjacent parts. It is this membrane which forms the velvety skin of the peach and of the plum. When the ovary is infra, that is, whenever it is united with the tube of the calyx, it is this tube which constitutes the epicarp. And then we always distinguish at its superior part the teeth or divisions of the limb, or at least a border formed by the remains of this part of the floral envelope, which fades after fecundation. The mesocarp is the parenchymatous portion in which all the vessels of the fruit are united. It frequently presents a very considerable thickness and a fleshy consistence, which has obtained for it the name of sarcocarp. as in the peach, the apricot, the cherry, etc., and constitutes the part we eat. Sometimes the mesocarp is dry and fibrous, as in the almond, or it constitutes the part called the shell, and at other times it is so thin as to be hardly distinguished. The endocarp, which internally lines carpels or ovaries and constitutes the layer of the pericarp nearest the seed, varies much. In most fruits it is thin and transparent, as in the husk of beans, for example. But at other times it becomes hard and brittle, and forms what is named the stone of the fruit. Each carpel has two edges, one named dorsal, which corresponds to the primary nerve of the appendage, and another called ventral, which results from the agglutination of these two edges to each other, and when the edges of the carpel, in place of being simply joined, are folded inwards, they constitute an internal partition which divides the ovarian cell or cavity into two parts. The carpels are sometimes single in each flower, sometimes more or less numerous, and in this last case they may be agglutinated to each other in different ways, and constitute compound fruits, the appearance of which varies. Sometimes they are very distinct externally, at other times are united with the torus and with the calyx in such a manner that no trace of external union can be seen, and constitute a simple fruit. In general, the cells of different carpels united into a single mass are perfectly distinct, and the compound fruit consequently presents as many cells as there are carpels. But sometimes the carpels are not closed along their ventral edge, and then the cells of all these organs communicate with each other and constitute a single cavity, of which the circumference only is more or less lobed. And it also happens sometimes that the partitions which separate the neighboring cells are in part destroyed by the progress of maturation, and all the cells of a compound fruit are united into a single cavity, the center of which is occupied by a species of column formed by the remains of the ventral edge of the carpels thus united. Often, one or more carpels abort and leave no trace of their existence. Finally, not only may the carpels of the same flower be united to each other, but sometimes those of neighboring flowers approximate, and become agglutinated in a single mass, and thus constitute what is termed an aggregate fruit. Figs and the cones of the pine tree are composed in this way. At the period of their maturity, fruits present still other important differences. Some are indehiscent, from the Latin in, not, and dehiscere, to gape wide open. That is, they do not open spontaneously. Others, on the contrary, open of themselves, and are called for this reason dehiscent. In simple fruits, the opening generally takes place at the agglutinated edges of the carpel, or by this and the dorsal edge at the same time, so that the fruit is divided into two pieces called valves. In the compound fruits, we sometimes see the different carpels separate and fall singly, then remain closed or open in the same way as the simple fruits. Sometimes also the back of each cell is torn without the carpels being separated. The differences that we have pointed out in the conformation of fruits and the principal variations of form which they present have led botanists to class them as follows. Classification of fruits. All fruits are included in three classes. The first class is composed of the simple or apocarpous fruits, formed of a single carpel or of several free carpels. The first division of this class includes what are termed dry fruits, having a thin pericarp and being but slightly furnished with juices, and generally contain only a small number of seeds. This division contains two varieties. The first are the indehiscent, simple fruits. Under this head, we have the three following forms. Caryopsis. Fruit, monospermatic, from the Greek monos, single, and sperma, seed, having one seed, and indehiscent, the pericarp of which is very thin and intimately connected with the seed, as wheat, barley, rice, oats, etc. Achene, or achenium, from the Greek a, without, and kaino, I gape. Fruit, monospermatic, and indehiscent, the pericarp of which is distinct from the proper covering of the seed, as in hemp, sunflower, etc. Gland or nut. Fruit, unilocular, from the Latin unus, one, and loculus, partition, seed vessel not separated into cells, and therefore monospermatic, from the constant abortion of all the ovules except one. The coriaceous, or woody pericarp of this one, presents at its summit vestiges of the limb of the calyx, and is enclosed, either partly or entirely, in a kind of involucrum called cupule, as in the oak. The second variety of the first division of the first class contains the three following dehiscent fruits: follicula, little bag, follicle. Fruit ordinarily membranous, opening longitudinally on the ventral surface, as the larkspur, senna, etc. Legume or husk. Fruit which is ordinarily membranous, elongated, and compressed in form, opens longitudinally, both by the ventral and dorsal structure at the same time, as peas, beans, etc. Lomentum. Fruit similar to a pod or legume, but contracted at different points, forming partitions which result from the cohesion of the two faces of the carpel, and opening by transverse sections, as in Cassia fistula. The second division of the first class contains fleshy fruits, having a thick, pulpy, and succulent pericarp. They are never dehiscent. It contains the two following forms: drupe. Fruit fleshy, enclosing a nut internally, the mesocarp being fleshy and very thick, and the endocarp coriaceous, or bony, as the peach, the apricot, the cherry, etc. Nut. Fruit similar to a drupe, but the mesocarp is less thick, and constitutes what is called a shell, as the fruit of the almond. Sometimes these fruits, in place of being isolated, are grouped together on a fleshy gymnophore, so as to resemble a compound fruit, as in the strawberry and raspberry. The second class is composed of fruits that are compound or syncarpous, from the Greek sun, with, and carpos, carpel or fruit. They are formed of several carpels of the same flower agglutinated together. The fruits of the first division of the second class are free, not being united to the calyx or paragon through the medium of the torus. The first variety contains the two following dehiscent fruits: silique or siliqua. Fruit, dry, analogous to a legume, but bilocular, from the Latin bis, two, and loculus, partition, and having the seeds attached upon the two edges of the partition in each cell, as the cabbage, rose, etc. Capsule. Fruit, dry, formed of two or more carpels, united together, and opening in different ways, but not bivalve, as the poppy. The second variety of the first division of the second class consists of the following indehiscent fruit: Hesperidae. Orange. Fruit, flesh, composed of a common epicarp, and several cells formed by the endocarp of different carpels, and filled with a sort of pulp, as the orange, citron, etc. The fruits of the second division of the second class are adherent, being united to the calyx or paragon through the medium of the torus. The first variety of this division contains fleshy or pulpy fruits. Pome or apple. Fruit composed of several indehiscent carpels with a cartilaginous or bony pericarp, completely enveloped by a fleshy indehiscent calyx to which they are agglutinated, as the apple, pear, medlar, etc. Melanide or pepo. Fruit, unilocular, formed of several indehiscent carpels with edges not enfolded, and enclosing numerous seeds surrounded by a pulp, as melons, gourds, etc. Berry. Fruit multilocular, indehiscent, semifluid internally, as gooseberries, etc. The second variety includes dry fruits and certain adherent capsules, etc. The third class is composed of fruits that are aggregated or polyanthocarpous, from the Greek polos, many, anthos, flower, and karpos, fruit. Fruit from many flowers. Because these fruits are formed by the approximation or agglutination of the fruits of many flowers, the three following are placed in this class. Cone, an assemblage of sessile fruits concealed at the base of convex scales formed by bracts, or by a ligneous pericarp, as the pine, savin, etc. Cycone, an assemblage of very small fruits, analogous to drupes, enclosed in a fleshy concave receptacle, as figs. Soros, an assemblage of fruits attached to a single body by means of their floral envelopes, which are fleshy and united so as to resemble a marmoladed berry, as the mulberry, etc. Of seeds. The seeds, which during the early period of their development are called ovules, are produced in the interior of the cells of the carpel or ovary, along the ventral suture of this organ. That part of the carpel from which the seeds spring is named the placenta or trophosperm, from the Greek trepho, I nourish, and sperma, seed, seed nourisher. And the stalk or thread by which the seeds are attached to it we call the funicula, Latin little cord, or podosperm, from the Greek pos, in the genitive, podos, foot, and sperma, seed, seed foot or seed stalk. The funicula, in general, resembles a little pedicle, and its extremity is expanded sometimes around the seed so as to envelop it more or less, and constitute what is named the aril, arillus. Sometimes this expansion of the funicula is thick and fleshy, sometimes thin and membranous. Its forms vary considerably. In the nutmeg tree, for example, the aril forms a fleshy lamina of a bright red, divided in shreds, which envelop the nutmeg, and constitutes the spice called mace. It is to be remembered that the aril is found only in those plants that have a monopetalous corolla. The seed itself is the part of the perfect fruit contained in the interior of the carpel, and encloses the body which is destined to become the new plant. The point by which it adheres to its funicula generally has the appearance of a small scar or cicatrix, and is called the hilum. Finally, the seed is composed of two series of organs, namely the accessory parts and the essential parts. The accessory parts of the seed are divided into spermoderm, from the Greek sperma, seed, and derma, skin, or episperm, from the Greek epi, upon, sperma, seed, and the albumen. The essential part is called the embryo. The spermoderm, or skin of the seed, is sometimes a simple membrane, and sometimes a covering composed of 2 or even 3 coats. the nutritious vessels of the seed, which come from the trophosperm, ramify in the thickness of this seed covering, and we usually perceive near the center of the hilum a minute hole, which gives them a free passage. The albumen, also called perisperm, from the Greek peri, around, and sperma, seed, or endosperm, from the Greek endon, within, and sperma, seed, the albumen is a body intermediate between the spermaderm and the embryo, which surrounds the latter, embryo, and ordinarily constitutes a depot of nutritive matter. In general, it is formed of a kind of cellular tissue, in which is found the fecula, as in wheat. At other times it encloses fatty matter, as in the castor oil plant, Palma Christi. Frequently it is very thin, and sometimes it is entirely wanting. The embryo, or essential part of the seed, is the rudiment of the new plant which the seed is destined to produce. In plants unprovided with albumen, or perisperm, the embryo constitutes a single kernel or almond, and fills the spermaderm. In this case we call it an epispermatic embryo, because it is covered immediately by the episperm, or an internal layer of the spermaderm. But in plants that are provided with an albumen, the kernel is composed of the latter united to the embryo. In this instance it is termed an endospermatic embryo. In this latter case, the position of the embryo may vary considerably. Sometimes it is simply applied upon the point of the surface of the albumen, which presents for its reception a little pit, fossette, as in the grain of wheat, or it may be rolled under the albumen so as to envelop it more or less completely. It is then said to be extra. At other times it is entirely enclosed in the interior of the albumen, and then takes the name of intra-embryo, as in the castor oil seed. We distinguish in the embryo, that is, in the young plant which is still enclosed in the seed, three principal parts: the radicle, the plumule, and the cotyledons. The radicle is the young root, which before germination is always simple, but by development it is more or less divided, and constantly tends toward the center of the earth. The plumule, or young stem, is sometimes scarcely visible before germination. At other times it is as long as the radicle, with which it is inferiorly continuous. By development it becomes elongated in a direction contrary to that of the root, and consequently it always tends to rise. We distinguish in it two parts, namely the stemule and the gemule, situate one above the other below the cotyledons. The cotyledons are lateral appendages which represent the first leaves. They are almost always thick and fleshy in plants unprovided with albumen, but thin and membranous in endospermatic seeds. Their use seems to be to furnish the young plant with the first alimentary matter, and their number is various. Sometimes there is but one, and at others there are two or more. Plants whose seeds contain only a single cotyledon are named monocotyledons, from the Greek monos, single, and cotyledon, seed lobe. Those whose seeds contain two or more cotyledons are named dicotyledons, from the Greek dis, two, and cotyledon, seed lobe. The annexed figure represents the section of a seed of a monocotyledon in process of germination, showing the perisperm, the summit of the single cotyledon, the base of the cotyledon forming a sort of tube. At the lower part of the base we see the plumule, which sets upon the radicle. Figure 125 represents the same seed further advanced in germination after the appearance of the plumule or young stem. When the seeds are ripe, or a short time afterwards, they separate from the plant. Sometimes the fruit opens spontaneously to permit their escape. At other times they are detached without its opening, and the pericarp is sown entire, or in part, with a seed. Most seeds fall upon the surface of the ground, and nature resorts to various means to secure their dispersion. Sometimes they are surmounted by a little plume which takes the wind. At other times they are furnished with wings, so as to be readily carried to a distance. They are often conveyed to great distances by the currents of rivers or of the sea, and occasionally their dissemination is effected in a still more singular manner, for it frequently happens that birds eat fruits, the seeds of which they do not digest, but afterwards discharge at some more or less distant place, where they germinate and grow. The number of seeds produced by most plants is so considerable that if every seed germinated, the product of some square leagues of land would be equivalent, according to several calculations, to the vegetation of the whole world. For example, 160,000 seeds have been counted on a single stalk of tobacco, and 629,000 on an elm. But this seeming prodigality on nature's part is only a wise precaution against the numerous causes of destruction to which they are exposed. Of germination. The term germination is applied to the series of phenomena that a seed presents in effecting the development of the embryo it contains. Germination cannot take place except under a concurrence of circumstances dependent on the seed itself and external influences. The seed must be ripe, enclose a complete embryo, and not be too old. There are some seeds that retain the faculty of germinating for a very long time. Wheat and beans enjoy this property for 60 and even 100 years, while coffee, on the contrary, loses it in a very short time. Some, when protected from contact with air, preserve their germinative faculty for a long period. On the other hand, the seed must be subject to the action of certain external agents, the chief of which are water, heat, and air. Water is indispensable to germination. It acts by penetrating the substance of the seed, by softening its envelopes, by causing the embryo to swell, and by bringing about in the endosperm or in the cotyledons chemical changes which render the substances deposited in their parenchyma, from the Greek parekeuin, to strain through, the spongy and cellular tissue of organized bodies, fit to nourish the young plant. Heat is also necessary. Below a certain temperature the seed remains inactive. Too much heat destroys the vegetative power. The extreme limits are between 32 and 120 degrees of Fahrenheit's thermometer. The presence of air is as indispensable to the germination of seeds, or at least to their development, as it is to the respiration of animals. It acts through the means of the oxygen it contains. Seeds placed in contact with this gas are stimulated in their germination. Light, on the contrary, hinders or at least retards it much. The first phenomenon observed in germination is the swelling of the seed and the softening of its envelopes. The time at which the latter burst vary in different plants. The manner of this rupture is either regular or irregular. From this moment we observe the embryo, which is at this period termed plantule, diminutive plant, begin to develop. We observe its two extremities, which constantly grow in opposite directions. The gemule, called the ascending caudex, is directed towards the air and light. The radicle, or descending caudex, tends to bury itself in the ground. The substance of the cotyledons liquefies. It becomes milky and serves for the nourishment of the plantule. The perisperm undergoes an analogous transformation and appears to perform the same function, while the radicle, by penetrating the earth, gives rise to delicate little ramifications. The stemule lengthens and rises up the cotyledons. The gemule is at once free and uncovered. The little leaves of which it is composed expand, increase in size, become green, and begin to draw from the atmosphere a portion of the fluids which nourish the young plant. The act of germination is now at an end, and nutrition goes on as we described it when speaking particularly of this function. All seeds do not require the same period of time for their germination. For instance, certain cresses germinate in 2 days, the turnip and bean in 3 days, lettuce in 4, the melon in 5, most of the grasses in 6 or 7 days, the hyssop in a month, the peach in a year, and rose tree in 2 years. What we have hitherto said of fructification relates entirely to cotyledonous plants, and we have still to say a few words of what takes place in acotyledons, from the Greek a, without, and kotyledon, seed lobe, in which we find neither flowers nor seed nor embryo. The class of acotyledons comprises all plants which are unprovided with true organs of generation, that is, stamens and pistils. On this account they are named cryptogamous, from the Greek kryptos, concealed, and gamos, marriage, or agamous, from the Greek a, without, and gamos, marriage, and are produced through the means of corpuscles analogous in their structure and development to the bulbils or bulblets of certain perennial plants. These corpuscles, minute bodies, are named sporules or seminules. They are contained in envelopes called conceptacles, and are variously placed either in the interior of the plant itself, or, but more rarely, on its exterior in the form of tubercles, as we shall see when we come to speak of the history of these plants. End of section 7.
Section 8 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Botany by William Ruskenberger. Lesson 6, Part 1. The Classification of Plants. As we stated when beginning the natural history of animals, we give the names of classification to any arrangement designed to facilitate the determining and study of objects, by separating them into more or less numerous groups, which in their turn are again divided and subdivided, and by assigning to each of these divisions a name and characters suitable to enable us to recognize all bodies of which they are composed. With this view, we make use of 2 kinds of classification, one called an artificial system, and the other a natural method. An artificial system, or classification of plants, is a mode of arrangement by means of which we may readily obtain a knowledge of the name of a plant by examining the characters furnished in the conformation of certain parts of these beings. In this kind of classification we divide and subdivide the vegetable kingdom into groups, into each one of which we range all those plants which possess a certain character, selected arbitrarily, and exclude all those that do not possess this same character, without considering whether we separate in this way plants that resemble each other in all the most important relations, or whether we bring together in the same division other plants that possess scarcely any property in common with each other. On this principle, we might class plants accordingly to the variations observed in the form and structure of the leaves, or of the corolla of the flower, or any other organ. But by proceeding in this way, we should learn almost nothing in relation to the organization of these beings, or in respect to the degrees of resemblance or dissimilarity they possess. A natural method, or classification, is, on the contrary, a sort of synoptical table of all the modifications that nature has produced in the conformation of plants, a table in which these modifications are arranged according to their relative importance, and serve for the establishment of divisions and successive subdivisions. In consequence of this, plants arranged according to this method have more important and more numerous points of resemblance to each other in proportion to their approximation to each other in the classification. For instance, when 2 plants are placed in 2 different divisions, It is because they differ from each other in more respects than either of them differs from all the other plants with which it is arranged, and these differences are less important between different species of the same genus than between the different genera of the same family. Those characters which distinguish the families from each other are, in their turn, of less importance than those employed to separate from each other the groups formed by the union of several of these families, and so on. By the assistance of these methods, we determine the name of a plant we wish to know with less facility than by an artificial system. But we acquire much more important knowledge, because having thus ascertained, according to the place a plant occupies in a classification of this kind, we know the principal features of its mode of organization, and, consequently, its physiological history also. Botanists have successively employed different artificial systems and the natural method in the classification of plants. Among the first there is one which, from its simplicity and the celebrity it for a long time enjoyed, merits being cited here. It is the system of Linnaeus, a Swedish botanist who died in 1778, which is based upon the differences that plants present in the various essential parts of their flowers, but especially in their stamens. In this system of classification, plants unprovided with stamens and pistils form a particular class, and those which possess these organs are divided, first according to the existence of stamens and pistils in the same flower, or in different flowers; second, according to the cohesion of the stamens to each other, or with the pistil, or according to their not cohering; third, according to the relative length of the stamens; fourth, according to the number of stamens, etc. The first 11 classes are characterized by the number of stamens. The names of these and the 2 succeeding classes are formed from the Greek by prefixing the proper numerals to the word aner, man, used metaphorically for stamen. Class number 1, Monandria, includes all plants with perfect flowers that have but one stamen. 2, Diandria, 2 stamens. 3, Triandria, 3 stamens. 4, Tetrandria, 4 stamens. 5, Pentandria, 5 stamens. 6, Hexandria, 6 stamens. 7, Heptandria, 7 stamens. 8, Octandria, 8 stamens. 9, Enneandria, 9 stamens. 10, Decandria, 10 stamens. 11, Dodecandria, 11 to 19 stamens. The 2 succeeding classes are characterized by the number of the stamens with their mode of insertion. 12, Icosandria, 20 or more stamens, which are attached to or stand upon the calyx, as in the apple, cherry, etc. 13, Polyandria, which do not adhere to the calyx, that is, the stamens are hypogynous. The 2 following classes are characterized by the relative length of their stamens. 14, Didynamia, from the Greek dis, 2, and dynamis, power, 2 long and 2 shorter stamens, as in the mint. 15, Tetradynamia, from the Greek tetra, 4, and dynamis, power, 4 long and 2 short stamens. The longer stamens are supposed to be the most powerful. The 4 following classes are characterized by the connection of their stamens. 16, Monodelphia, from the Greek monos, single, and delphos, brotherhood, having the filaments of all the stamens united into a set or tube, constituting a single brotherhood. Example, the mallow. 17, Diadelphia, from the Greek dis, 2, and delphos, having the filaments of the stamens united in 2 sets, as in the pea. 18, Polyadelphia, from the Greek polis, many, and delphos, having the filaments of the stamens united into more than 2 sets. 19, Syngenesia, from the Greek sun, together with gynome, to arise, to grow, having the stamens united by their anthers in a ring or tube, as in the sunflower. 20, Gynandria, from the Greek gyne, woman, used metaphorically for pistil, and aner, stamen, having the stamens in appearance growing out of the pistil, as in the lady slipper. In all the preceding classes the flowers are perfect. The next 3 classes are characterized by the stamens and pistils being separately contained in different flowers. 21, Monoecia, from the Greek monos, single, and oika, house, the stamens and pistils are in separate flowers, but both grow on the same plant or both dwell in the same house, as the name denotes. 22. Dioica, from the Greek dis, two, and oika. The stamens and pistils are not only in separate flowers but on different individuals. They are in two households. 23. Polygamia, from the Greek polis, many, and gamos, marriage or union. The stamens and pistils are separate in the same flowers and unite in others, all on the same, or on two or three, individuals of the same species. The last class includes flowers in which neither stamens nor pistils are visible. They are now termed flowerless plants. 24. Cryptogamia, from the Greek kryptos, concealed, and gamos, marriage, having the essential organs of the flower concealed from view. In the first 13 classes of the Linnaean system, the orders are founded on the number of styles, and when these are wanting, on the number of stigmas. The names of these orders are formed by prefixing numerals from the Greek to the word gyna, from gyne, woman, metaphorically used for pistil. Order 1. Monogyna, one style or sessile stigma. 2. Digyna, two styles or sessile stigmas. 3. Trigyna, three styles or sessile stigmas. 4. Tetragyna, four styles or sessile stigmas. 5. Pentagyna, five styles or sessile stigmas. 6. Hexagyna, six styles or sessile stigmas. 7. Heptagyna, seven styles or sessile stigmas. 8. Octagyna, eight styles or sessile stigmas. 9. Enneagyna, nine styles or sessile stigmas. 10. Decagyna, 10 styles or sessile stigmas. 11. Dodecagyna, 12 or about 12. 12. Polygyna, more than 12. The 6th, 7th, 8th, and 9th orders are very rarely found. The 14th class, Didynamia, contains two orders, named and characterized as follows. Gymnospermia, from the Greek gymnos, naked, and sperma, seed, has naked seed, commonly 4 in number. Angiospermia, from the Greek agion, a vessel, and sperma, seed, has the seeds which are usually numerous enclosed in a seed vessel. The 15th class, Tetradynamia, has two orders, distinguished by the form of the fruit. Siliculosa, fruit a silical or roundish pod. Silicosa, fruit a silique. The orders of the 16th, 17th, and 18th classes are founded on the characters of the first 13 classes. For example, the mallow, which belongs to the 16th class, Monodelphia, has more than 20 stamens, and therefore belongs to the order Polyandria of that class. The 19th class, Syngenesia, has 5 orders, characterized by the nature of the florets, whether perfect, separated, or barren. 1. Polygamia aequalis, has perfect florets, that is furnished with both stamens and pistils, example, the thistle. 2. Polygamia superflua, has the florets of the disc perfect, and those of the ray furnished with pistils only, example, the aster. 3. Polygamia frustrania, has the florets of the disc perfect, those of the ray without either stamens or pistils, which are well formed, example, the sunflower. 4. Polygamia necessaria, has the florets of the disc with stamens only, the stigmas being imperfect, and those of the ray with pistils only, example, Silphilium. 5. Polygamia sagrata, has all the florets perfect, and each floret has a well-formed calyx, the whole being enclosed in an involucra, example, Elephantopus. The orders of the 20th, 21st, and 22nd classes are for the most part characterized by the number of stamens. The 23rd class, Polygamia, has 3 orders founded on the immediately preceding orders. 1. Monoecia, has both separated and perfect flowers on the same individual. 2. Dioica, when one individual bears the perfect, and another the 2 kinds of separated flowers. 3. Trioica, when one bears the perfect, a second the staminate, and a third the pistillate flowers. The ferns, mosses, algae, fungi, etc., constitute the orders of the 24th class, Cryptogamia. The basis of the natural method was proposed by a French botanist, Bernard de Jussieu, and this classification, perfected by the labors of Antoine Jussieu and the botanists of his school, is the one now generally adopted. According to this classification, we bring together in groups, called genera, all the species of plants which resemble each other throughout in the important characters of their organization, and in the same manner we bring together into divisions of higher rank, named natural families, the different genera, the most essential organs of which possess an analogous mode of structure. Then we group together the natural families according to the same principle, and finally obtain a small number of divisions which comprise all the subdivisions we have mentioned above, and which by their union include the whole vegetable kingdom. The most important differences among plants consist in the absence or presence of flowers or organs of fructification, and this difference almost always coincides with their peculiar modes of organization in all their parts, such as the absence or presence of distinct vessels in the tissue of the plant. Therefore, in a natural method, we must first divide the vegetable kingdom into two groups, one containing plants which are reproduced by means of flowers, and the other including plants which are not multiplied in this way, and unprovided with flowers. This is in fact the course followed. We ordinarily designate the first of these divisions under the name of cotyledonous or phanerogamous plants, and the second under the name of acotyledonous or cryptogamous plants. The phanerogamous plants, from the Greek phaneros, evident, and gamos, marriage. The phanerogamous or cotyledonous plants all resemble each other in the most important particulars of their organization, but nevertheless very greatly differ from each other. In some the seed contains but a single cotyledon, and the stem is endogenous. The others have seeds provided with two or more cotyledons, and an exogenous stem. Consequently, we divide them into two groups which are called monocotyledons and dicotyledons. Among the cryptogamous plants, there are some which are composed exclusively of cellular tissue, and do not possess any distinct organs that are analogous either to roots, stems, or leaves. There are others, although composed chiefly of cellular tissues like the first, often acquire vessels at a certain period of their development, and are provided with parts analogous to the roots and leaves of ordinary plants. In order that the classification of these plants be natural, that is, the expression of the more or less important resemblances or differences they present, we must therefore form them into two divisions, that of cellular plants, properly so called, and that of semivascular plants. We subdivide the monocotyledonous and the dicotyledonous plants into classes according to the structure of their flowers, and to characterize the groups thus formed we ordinarily take into consideration first the absence or existence of a corolla, etc. Then we make a distinction between the monopetalous and the polypetalous corolla. Then we consider the manner of insertion of the stamens or petals when they possess stamens. Finally, the classes thus formed are subdivided into natural families according as nature has variously modified the general mode of organization of the seed, of the fruit, of the flower, etc. Cryptogamous plants. Cryptogamous plants are constituted exclusively or chiefly of cells, and during the first period of their growth, or even throughout their existence, are unprovided with vessels or stigmata. They also differ from phanerogamous plants in their mode of propagation, for their multiplication always takes place without the aid of various reproductive organs analogous to stamens and pistils, and is effected by division or by the development of sporules, bodies which resemble the seeds of ordinary plants, but have no protecting envelope like a pericarp, nor a depot of nutritive matter similar to the albumen or to cotyledons. We divide these plants into two groups, cellular plants, properly so called, and semivascular plants. Cellular plants, properly so called, are composed exclusively, and at all periods of their existence, of cellular tissue, which forms a homogeneous mass which is rarely green, and its forms, which are very various, do not at all resemble those of ordinary plants. We can distinguish in these plants neither roots nor organs similar to stems or leaves, and absorption seems to take place throughout the whole extent of their surface. When their tissue is membranous and flat, we give the part thus constituted the name of thallus, and when branched and spread out, it constitutes what is called a frons. The sporules are sometimes naked, sometimes contained in one or more membranous sacs which seem to be ordinary cells. This group is divided into three natural families: lichens, fungi, and algae. Lichens are perennial plants which grow upon the trunks of trees, on rocks, or on the surface of the ground, and are composed of a thallus, possibly from the Greek thalliae, the blooming one, having the appearance of filaments or foliaceous membranes, or hardened pulverulent crusts. This thallus consists of two layers, one external or cortical, variously colored but never green, and an internal or medullary, which often contains green matter and gives origin to young plants, either by the division of its tissue or by the production of spores, from the Greek spora, seed, called apothecum or scutum, Latin, a shield, because their form is frequently like that of a small shield. There are more than 2,000 species of lichens known. They grow in the most arid places and constitute the greater parts of the vegetation of the regions near the pole. One species, the Cenomyceae rangiferina, reindeer, Cenomyceae, from the Greek kinos, empty, and mucase, a minute fungus, forms the food of the reindeers of Lapland for the greater part of the year, and several are used as dyestuffs, as the archil. The fungi. The fungi mushrooms are plants of various forms and are never green. In general, they consist of cellular tissue formed into globular masses, or having a peduncle, surrounded by a cap, pileus, which is ordinarily convex, and the inferior surface is furnished with radiating laminae. They are distinguished from lichens and algae by the absence of fronds or crust, bearing organs of fructification. The sporules are sometimes naked and sometimes enclosed in little capsules. In common mushrooms, the union of these capsules constitutes a membrane named the hymenium, from the Greek oumen, a membrane, which is ordinarily plated and covers entirely or in part the surface of the plant. These sporules become free, sometimes by the rupture of their envelope, sometimes by the decay of the tissue which surrounds them, and when they germinate, we observe arising from them white filaments, upon which springs bodies from point to point, which seemingly constitute the mushroom. But in reality they appear to be only the spores, that is, the reproductive organs. These plants are developed in general in shady, damp, and warm situations, and are found especially numerous where organic matter in a state of putrefaction abound. Many live as parasites upon perennial plants, and some grow on the surface of water, but most of them inhabit the surface of the earth or are buried in the soil. Sometimes they grow with extraordinary rapidity. Frequently we see thousands of mushrooms growing up in a single night, and the greater part of them do not live beyond a few days at most. There are some, however, that grow slowly and live many years. This family is very numerous, and is divided into several groups, the most important of which are the agarics, or mushrooms properly so called, Lycopodiceae, and the Muscadiniae. Moss tribe. Agarics, or mushrooms properly so called, are plants ordinarily of fleshy consistence, the sporules of which are placed on the surface of an external membrane and enclosed in distinct capsules. Some have a sort of stem surmounted by a sort of umbrella-shaped cap, the inferior surface of which is lined by the sporiferous membrane. Others are club-shaped or branched. Others again form irregular masses of a gelatinous consistence. They are commonly found in shady, damp woods at the foot of old trees, and a great many are known. Several of them may be used as food and are even very much esteemed, but others are violently poisonous, and there are no general characters by which good mushrooms may be certainly distinguished from bad ones. It is only when we are able to recognize perfectly the species known to be good that we should venture to eat those found in forests, because there are poisonous mushrooms which so closely resemble the edible species that mistakes are easily made. We should invariably reject those which change color quickly after being gathered, those which contain a milky juice, or are of a very soft and watery structure, those that have a peppery, bitter, or astringent taste and disagreeable odor. A bright red color is also frequently an indication of poisonous qualities. The symptoms of poisoning produced by mushrooms do not appear immediately after they have been introduced into the stomach. They do not supervene until the end of 5 or 6 hours, or sometimes even longer after eating. The patients experience nausea, almost continual and very acute pains. They have frequent vomitings and numerous evacuations. Thirst cannot be appeased. The pulse is small, hard, and frequent. At a later period, partial or general convulsions take place, swooning, cold sweat, and drowsiness. Most generally, the intellectual faculties contain unimpaired till death terminates the case. The mushrooms most used as food are the edible agaric, Agaricus edulis, the Mauserum agaric, the orange, chanterelle, morel, ceps, or Boletus edilis, or edible bowl. But the only species cultivated is the edible agaric. which are propagated at pleasure by means of the white filaments that spread out in the soil where the sporules have germinated, and are known to gardeners under the name of white of mushrooms. One of the most poisonous mushrooms is the false orange, which resembles the true orange, which is among the most esteemed species, and is very common in the south of France. Tinder, or spunk, is a species of mushroom of the genus Agaric. The division of the Lycopodiaceae comprises mushrooms, the sporals of which are not enclosed in especial capsules. We place among them truffles, singular plants of irregularly rounded form, which grow underground without being attached to any other body, and without ever appearing above the surface. The edible truffle, so much esteemed by gourmands, is of a brown color, strong odor, and peculiar taste. Its size varies from that of an egg to that of a fist, and it grows 5 or 6 inches underground. It is chiefly met with in forests of ash, chestnut, or oak, and in the soils composed of sand and clay. To gather these subterranean mushrooms, we take advantage of the instinct of hogs, which root them up with their snout. They have not been multiplied by cultivation as yet. The Mucidinae, or molds, are also plants of the family of fungi, and we also place in this natural division certain parasitic plants that grow on other living plants, often producing in them very remarkable injurious alterations. Of this number is a species of fungus named aredo, which is sometimes developed on wheat, and occasions what farmers call blight. The family of algae, seaweeds, is composed of marine and other aquatic plants, the structure of which is very simple. The fuci, which cover the rocks on our coast, belongs to this group. The genus Fucus yields iodine, a useful medicine. The Chondrus crispus, or carrageen moss of Ireland, which also grows on our own coast, is converted into size. It also yields a fine jelly for invalids, and is often used in the composition of blancmange. The semivascular plants are at first composed of cellular tissue alone, like cellular plants, but often acquire, at a certain period of their development, vessels and stomata, like phanerogamous plants. They are provided with roots like the latter, and with expansions or fronds, ordinarily green, analogous to leaves. The latter often arise from an axis, similar to a stem, and sporules are developed upon their external or inferior surface. In this division we place the mosses, Massae, the ferns, Felices, and some other families of less importance. The mosses, Massae, have a very short herbaceous stem fixed on the ground on stones or the barks of trees by small brown roots, and covered by little leaves in form of scales. There are no vessels in their interior. Finally, their spores are enclosed in lateral or terminal buds, surrounded by a sort of paragon, and rise from the internal parietes of a sort of urn. Mosses rank among the smallest of plants. They seldom exceed the height of a few inches, and many are so minute they would wholly escape our observation if they did not grow in patches. Several species, indeed, are scarcely visible to the naked eye, and yet they have a stem, leaves, fruit, and other organs as the largest plants of the family. Gray's Elements of Botany. The ferns, Felices, are herbaceous or arborescent plants, the fronds or leaves of which are alternate, often lobate, and grow upon a sort of vertical stem or rhizome. We find stomata on the leaves and trachea, and other vessels in their petioles. Their organs of fructification are found on the interior surface of the leaves, towards the edge of the extremity of the veins. Although the ferns of the United States, and of all northern climates, have prostrate stems, and consequently do not rise at most above 3 or 4 feet in height, yet in tropical countries their trunks are often erect, and frequently attain the height of 70 or 80 feet. The tree ferns of the tropics are said to be objects of incomparable beauty, their straight, unbranched trunks often rising, like those of palms, as high as 40 or 50 feet, without a leaf. Gray. We also place in this division of the vegetable kingdom the chara, an aquatic plant which is very remarkable on account of the singular circulation observed in the interior of the cellules of its tissue. Of the structure of the charae, very little is certainly known. They consist of the submersed water plants, having slender jointed stems, destitute of leaves, but furnished with whorled branches resembling the stem. There are only a few species, but these abound in stagnant waters. End of section 8.
Section 09 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by J.E.D. Klein. The Elements of Botany by William Ruschenberger, Lesson 6, Part 2. Phanerogamous plants. This great division of the vegetable kingdom comprises all plants that bear flowers and are multiplied by means of true seeds. They are also called cotyledonous plants because the embryo or germ contained in the seed is always provided with one or more cotyledons, organs which serve as depots of food for the nourishment of the young plant during the first part of its existence, and are not found in the cryptogamia. Vessels as well as cellular tissue always enter into the composition of these plants, and for this reason, botanists sometimes designate them under the name of vascular plants. They are divided, as we stated before, into two groups, the monocotyledons and dicotyledons. Monocotyledonous plants. The most remarkable characteristics of the organization of plants of this division are: first, the existence of a single cotyledon in the seed, a circumstance which corresponds with a particular mode of germination. Second, the existence of an endogenous stem, that is, a stem in which the new fibers do not form concentric layers around the old, but are arranged in scattered bundles. Third, the arrangement of the nerves of the leaves is almost always parallel, as in Indian corn. Fourth, the existence of a single floral envelope called perianth or glume, which takes the place of calyx and corolla. These plants are also distinguished from the dicotyledons by their aspect and by some other characters. We place in this group the Gramineae, Palmaceae, Asperginae, Lilaceae, Narcissae, Prideae, Orchidae, and several other natural families. The family of Gramineae, grasses, belongs to the class of monocotyledons, with stamens inserted below the ovary, named for this reason monohypogynia, from the Greek monos, single, hupo, below, and gun, woman, metaphorically pistil, that is, having the stamens fixed below the ovary. They are for the most part herbaceous plants. Their stem, which is cylindrical and ordinarily hollow, presents at different points knots from which the leaves arise. It is called a culm, or straw. The flowers are generally united in a spike or in panicles. Their ovary is simple, and the seed, sometimes naked, and sometimes furnished with an envelope named glume, is composed of an albumen or farinaceous perisperm, having a lateral pit near its base which lodges the embryo. It is this perisperm which renders many of these plants so useful, by furnishing to man an abundant and wholesome article of food, flour, and meal, etc. This family is composed of a great many genera, among which are wheat, rye, barley, oats, maize, Indian corn, rice, and sugar cane, as well as bamboo and reeds. We also place in this family different herbs, which constitute the bottom grass of all natural prairies, such as fescue, alopecia, from the Greek alopex, a fox, and aura, tail, foxtail, timothy, festica, meadowgrass, and darnel or terror. Common wheat, triticum, the most important of all the grasses, is an herbaceous annual plant with a stem, culm, 4 or 5 feet high, furnished with some leaves, which is terminated by a spike composed of flowers united in groups of from 3 to 6 called spikelets, in a common envelope, which consists of 2 scales bearing the common name of glume. Each flower bears 3 stamens enclosed between 2 unequal palliae, from the Latin palliae, chaff, and the external of which often but not always terminates in a long beard or barb called on. The seed is oval, larger than that of most other grasses, convex on one side, and on the other hollowed by a longitudinal groove. On an average, there are 40 seeds on each spike. It is filled by a white, farinaceous substance, chiefly consisting of fecula and a peculiar substance named gluten. These two substances, crushed by a millstone, constitute the flour which we use for making bread. Fecula consists of minute grains filled with a matter of gummy consistence, which, by the action of heat and various chemical agents, burst and permit their contents to escape. This is the reason why, when we boil fecula in water, it suddenly thickens and becomes paste. Gluten is a very elastic substance, which may be separated from fecula by washing wheat flour wrapped in a cloth under a stream of water for some time. Wheat is sown at two different periods, in the autumn and in the spring. The first is called winter or fall wheat, and the second spring wheat. The season of the harvest varies according to the climate. There is a species of wheat called spelt, the seeds of which are not separated from their envelope by thrashing, and still another called dog or couch grass, having a long, spreading root, which is very injurious on account of the rapidity with which it overspreads wheat fields. Common rye, sakale, very much resembles wheat, but it never has more than 2 flowers joined in the same glume, and forming a spikelet. It is said to have come originally from the Levant, but is cultivated in the United States and all parts of Europe. It succeeds better than wheat in cold countries and in dry and arid soils. It is sown earlier than the other cereals and generally flowers in the month of May, and it is usually gathered 15 or 20 days before the wheat, generally in the month of July. Rye flour is not so white as that of wheat, but is used for the same purposes. Barley, hordeum, is distinguished from the preceding species by its simple compact spike, formed of spikelets of a single flower, arranged 3 and 3. Its height does not exceed 2 or 3 feet. It is the easiest of the cereals to cultivate, and the most rapid in its development. But barley flour is even less nourishing than rye. What is called pot barley is made by grinding off the husk, and pearl barley is made by carrying the operation so far as to produce roundness of the grains. Malt is the chief purpose for which barley is cultivated in Great Britain and the United States. In order to understand the process of malting, it may be necessary to observe that the cotyledons of a seed, before a young plant is produced, are changed by the heat and moisture of the earth into sugar and mucilage. Malting is only an artificial mode of effecting this object by steeping the grain in water and fermenting it in heaps, and then arresting its progress toward becoming a plant by kiln drying it, in order to take advantage of the sugar in the distillation of spirits, or fermentation for beer. Oats, avena, has its flowers arranged in an open panicle composed of multiflorous spikelets hanging on their pedicles. The seeds adhere to the glume and are oblong and acute. They are much used as food for horses. Oats are sown in the autumn or spring and are gathered from the middle of July to the 1st of September. The flour, called oatmeal, is also made into bread and forms what is termed groats by grinding off the husk. Rice, rhiza, also has flowers arranged in a panicle, but the spikelets are uniflorous. It is an annual plant and delights most in low, humid situations, and even in inundated places. Its culm rises 3 or 4 feet high, and its leaves are very long. It is originally from India. It is cultivated in Italy, but Asia, Africa, and America furnish most. Carolina rice is considered amongst the very best. It constitutes the principal article of diet of all the nations of the East. Maize, or Indian corn, zea, from the Greek zeb, I live, is also an herbaceous annual grass. Its fibrous roots give rise to 1 or more stems 5 or 6 feet high, the summit of which bears a panicle nearly a foot long. formed of male flowers in great numbers on several spikes. The female flowers are very numerous, sessile, attached upon a common axis in the axil of the superior leaves. The grains are rounded, of the size of a common pea, ordinarily of a yellow color, compressed one against the other, and arranged longitudinally in 6 or 8 rows. This plant is originally from America, but was long ago introduced into Europe and is cultivated in all the south of France, Spain, and Italy, and is used as food both for men and many domestic animals. Sugarcane, Saccharum, also belongs to the family of Gramineae. Its white silky flowers, all of which are hermaphrodite, are arranged in fasciculated spikes with 2 flowers at each articulation. Its stem, which is from 8 to 12 feet high, is full of sweet juice, which, being compressed and evaporated by boiling, yields sugar. It grows in the East and West Indies, United States, South America, and South Sea Islands. The cane in the West Indies is propagated by cuttings from the root end, planted in hills or trenches in spring or autumn, something in the manner of hops. The cuttings take root at the joints underground, and from those above send up shoots, which, in from 8 to 14 months, are from 6 to 10 feet long, and fit to cut down for the mill. A plantation lasts from 6 to 10 years. Sugar mills are merely iron rollers placed vertically or horizontally, between which the canes are passed and repassed. The juice thus squeezed out is collected and boiled with quicklime, which imbibes the superfluous acid which otherwise would impede crystallization. Impurities are skimmed off, and the boiling is continued till a thick syrup is produced, when the whole is cooled and granulated in shallow vessels of earthenware, which permit the molasses, a part that will not granulate, to drain off. It is now the brown or raw sugar of commerce. A further purification is effected by dissolving it in water, boiling, skimming, adding lime, and clarifying from the oily or mucilaginous parts by adding blood or eggs, which incorporate with them and form a scum. When boiled to a proper consistency, it is put into unglazed earthen vessels of a conical shape, with a hole at the apex, but placed in an inverted position, and the base, after the sugar is poured in, covered with clay. When thus drained of its impurities, it is taken out of the mold, wrapped in paper, and dried or baked in a closed oven. It is now the loaf sugar of the shops, and according to the number of operations it undergoes, is called single or double refined. The operation of refining is seldom or never performed by the growers, but forms a separate branch of business. Sugar candy is formed by dissolving loaf sugar in water over a fire, boiling it to a syrup, and then exposing it to crystallize in a cool place. When crystallized upon strings put into the syrup, it is called rock candy. This is the only sugar esteemed in the East. Barley sugar is a syrup from the refuse of sugar candy, hardened in cylindrical molds. Rum is distilled from the fermented juice of sugar water. The bamboo, bambusa, from the Indian name bambos, an arborescent plant of the equatorial regions, also belongs to the family of Gramineae. The bamboo is applied to a great variety of purposes. In India it is used for building houses and bridges, for masts, for boats, for making boxes, baskets, cups, mats, tables, chairs, fences, paper, and a variety of other purposes. And the tops of the tender shoots are, in the West Indies, pickled. It grows about 40 feet high. The genus Bambusa belongs to the class Exandria, order Monogynia of Linnaeus. The family of palms, Palmaceae, is composed of monocotyledons with perigynous stamens. The stem, which is cylindrical and resembles a column, is crowned by a fasciculus of large leaves. We have already spoken of its structure. Their flowers, which are generally unisexual, form catkins or a great bunch called raceme. The fruit is a fleshy or fibrous drupe containing a very hard, bony nut. Nearly all these large, beautiful trees belong to the intertropical regions. Many of them furnish the inhabitants of the countries in which they grow naturally wholesome and pleasant food. The date tree and the coconut yield excellent fruits. The cabbage tree palm bears a terminal bud which may be compared to our common cabbage, and several other species yield a fecula named sago. By incision into the space at the top of the stems of some, a saccharine liquor termed sweet toddy is procured, which when fermented constitutes palm wine and yields by distillation arrack or rack. The date tree, phoenix, the Greek name of the date, furnishes a great part of the diet of the inhabitants of Arabia and part of Persia. They make a conserve of it with sugar, and even grind the hard stones in their hand mills for their camels. The leaves are manufactured into baskets, bags, brushes, etc., and the stem is used in building, and another part of the plant is made into rope and rigging for small vessels. The palms of Scripture are the leaves of the date tree. The genus Calamus, from the Greek kalmos, a reed, furnishes the several species of rattan canes, whose flexible stems when split are woven into chair bottoms. The family is Asphodelae or Asperginae, belongs to the class of Monoperginae, and is composed of herbaceous plants with fibrous roots, the fruit of which is a capsule with 3 cells, or a globular berry. Common asparagus, the young shoots of which are eaten, is the type of this group. The family of Lydaceae is also placed in the class of Monoperginae. It is composed of plants with bulbous or fibrous roots, and the stem or shaft generally naked. The leaves are sessile or sheathing. Several species of this family are remarkable from having flowers with a colored calyx, such as the lilies, tulips, hyacinths, tuberoses, imperials, etc. The family of Amaryllidae or Narcissae and the family of Eridae belong on the contrary to the Monoepigynia. Among the first is the common narcissus, the Agave americana, and among the second the Iris florentina, which furnishes orris root, and the Crocus sativus, which has long, orange-colored stigmas, which, when dried, form saffron. The plants of the family of Eridae are herbaceous, under shrubs, with fibrous or bulbous roots. Generally their flowers are large, beautiful, and variegated in different colors. Dicotyledonous plants. The plants of this division are chiefly characterized, first, by the existence of an embryo with 2 cotyledons. Sometimes, however, we find 3 or even more. Second, by the internal organization of the stem, all parts of which are arranged in concentric layers, the growth of which is exogenous. Third, by the arrangement of the leaves, the nerves of which are ramified. Fourth, by the very frequent presence of both a calyx and a corolla, etc. They are divided into 4 groups: the apetalae, monopetalae, polypetalae, and dicotyledonnae. Apetalous dicotyledons. This group of dicotyledonous plants is characterized by the absence of a corolla, or at least of a double floral envelope, for the perianth as often resembles a corolla as a calyx. We place it in the Aristocolae, Lauridinae, etc. The family of Aristolochia, birthwort, from the Greek erisos, excellent, and lochos, female, because it was supposed to be excellent for females in particular conditions, is composed of twinning plants with epigynous stamens, with alternate and internal leaves, some species of which are cultivated in gardens. The common Aristolochia, for example. The Aristolochia serpentariae, Virginia snakeroot, belongs to this family. The family of Laurinae, from the Latin laurus, the laurel or bay tree, belongs to the class of Peristaminae, from the Greek peri, around, and stamen, and is composed of trees or shrubs with persistent leaves and fleshy fruit. The type of the family is the laurels, one species of which, the laurel of Apollo, is originally from Greece and was used by the ancients for decorating the crowns of their conquerors. Cinnamon is the bark of another species of laurel which grows in India, and camphor is derived from another tree of the same genus. We will also mention in this class the family of Chenopodiae, from the Greek chen, a goose, and pous, foot, goosefoot, because we find in it one of the plants which at present occupies a good deal of attention among agriculturalists, especially in France, namely the sugar beet. This plant, originally from the southern parts of Europe, is annual or biennial. It has a spindle-shaped, fleshy root, sometimes as thick as one's leg, which contains a considerable quantity of sugar, precisely like that of the sugar cane. The leaves of the sugar beet constitute an abundant and wholesome food for cattle, but it is especially cultivated in France for its sugar. Monopetalous dicotyledons. This division, which is much more numerous than the preceding, is characterized by having a corolla distinct from the calyx, and composed of a single piece. In it we place the Solanae, Primulaceae, Jasminae, Labiae, Synanthiae, Rubicaceae, etc. The family of Solanae is composed of monopetalous, dicotyledonous plants with hypogynous stamens, the flowers of which have a monosepalous, persistent calyx with 5 lobes, a regular corolla divided into from 4 to 5 lobes, 4 or 5 stamens, and a style bearing a stigma with 2 lobes, the fruit of which is a capsule or berry containing a great many seeds, and the leaves are commonly alternate. Most of the Solanae contain a narcotic, stupefying substance, which sometimes renders them very dangerous. Tobacco, henbane, stramonium, Jamestown weed, are of this kind. We find it even in the leaves of the common nightshade, and the Solanum tuberosum. This last plant, the stem of which is herbaceous, and the flowers white or slightly violet, has at irregular intervals on its long fibrous roots large tubers which are ordinarily rounded or oblong, which contain an immense quantity of fecula, and are known under the name of potatoes. The potato is originally from America, growing at this time wild in Mexico and Peru, and was first introduced to Europe by Sir Walter Raleigh about the year 1587, who carried it to England, whence it was soon spread upon the continent. It is now cultivated in almost every part of the world. This plant may be reproduced and multiplied in 2 ways, namely by the seed, or by the development of the root buds or eyes, which we see on the surface of the tubers. By sowing the seed we obtain a great variety, but the multiplication by the root buds produces, without any alteration in the form of color, potatoes like those from which the tubercles were taken. This last mode of culture is most generally used, and to succeed, it is only necessary to place entire tubers in the ground. We may divide them into several pieces, provided each fragment has 1 or more root buds upon it, for the development of which the feculent matter of the potato furnishes the nourishment. In those countries where frosts are feared in the spring, these vegetables are planted about the month of April, and gathered towards the end of October. A sandy and rich soil suits them best. In moist clay land they become pasty. By the ordinary method of cultivation, the potato yields but 7 or 8 for 1, but by hoeing the stems, that is, by heaping up the earth to a certain height around them, we obtain 12 or 13 for 1, and we are assured that by bedding and covering them with earth, the product may be increased to 60 for 1. Tobacco, Nicotiana tabacum, is a plant of the genus Nicotiana, which is a native of America. It is actively cultivated for its large leaves, the uses of which are known by everybody. Introduced into the stomach, it acts as a poison, and the smoke it yields when burnt commonly excites nausea and giddiness in persons not accustomed to it. But they may become really habituated to its use, which, either in the form of snuff, cigars, or smoking and chewing tobacco, has become almost universal. It is now cultivated in France and in most countries of Europe and several parts of India, as well as in various parts of America. It is sown about the month of March, and about the middle of July they begin to gather the leaves. This harvest continues into the period of frost, which the plant does not resist, and after drying the leaves thus obtained and having removed from them the large nerves, or stems, they are sprinkled with salt and water and for a certain time permitted to ferment. The tobacco for smoking is then coarsely cut up and exposed to a moderate heat which curls it. Tobacco for snuff is cut into strips which are pressed into masses, which are afterwards reduced to powder by a mill. Belladonna, Atropa belladonna, is another plant of the family Solanae which is also very poisonous. It is common under walls and in the woods. Its stem is branching, 3 or 4 feet high and slightly hairy. Its leaves are large, ovate, acuminate, and diffuse a disagreeable odor. Its corolla, in form of an elongated bell, has 5 lobes, is of a dull red. Its fruit is fleshy, about the size of a cherry, at first green, then reddish, and lastly black. It then resembles a black-heart cherry. Its taste is insipid, but this fruit is extremely poisonous. The henbane, Hyoscyamus, bittersweet dulciama, and several other plants of the same family are also active poisons. The family of Jasminae, also, belongs to the class of the Hypocorollae, and is composed of trees and shrubs with, commonly, opposite leaves. The corolla of the flower has 4 or 5 lobes, but only 2 stamens. We place in it the jasmine, olive, ash, etc. The olive, Olea europaea, is a tree originally from Asia Minor and the south of Europe, now extensively cultivated in the southern departments of France. In the east it grows from 40 to 50 feet high, but in France it rarely exceeds 25. It is extremely long-lived. Its leaves are opposite, lanceolate, of a bronze-green color above and whitish below. Its flowers are small and arranged in little clusters. Its fruit is a fleshy oval drupe containing a nut with a single seed. A symbol of peace and consecrated to Minerva, this tree was an object of a species worship among the Greeks, and its destruction was prohibited under severe penalty. It is still cultivated with care, but, for other reasons, its fruit and its oil. Olive, or sweet oil, may be said to form the cream and butter of Spain and Italy. Olive oil is made by crushing the fruit to a paste, then pressing it through a woolen bag, adding hot water as long as any oil is produced. The oil is afterwards skimmed off the water and put in tubs, barrels, and bottles for use. Pickled olives are prepared from unripe fruit by repeatedly steeping them in water, to which quicklime or any alkaline substance is sometimes added to shorten the operation. Afterwards they are soaked in pure water, and then taken out and bottled in salt and water, with or without an aromatic. Spanish olives differ from the French in consequence of being prepared from ripe fruit. The ash, Fraxinus, is among the largest and most beautiful forest trees. It delights in a humid, light soil. Its wood, which is white, longitudinally veined and very pliant, is much employed in carriage building, etc. The manna ash, or roundleaf ash, Fraxinus ornis, which grows in Calabria and on the coast of Africa, permits a sugar-like substance to exude through its bark, which hardens in the air and is known under the name of manna. Family of Lapiaceae belongs to the same division as the preceding. These plants, which are almost all herbaceous, have a square stem and a tubular corolla divided into 2 lips, one of which is superior to the other. The fruit is composed of 4 monospermous achynems enclosed in a persistent calyx, and the leaves are sessile and opposite. Most of the Labiataceae are very aromatic. They are employed in medicine and for the preparation of scented waters. Such are the mint, lavender, rosemary, sage, thyme, balm, etc. The family of Boraginae is closely allied to the Labiatae. The type of this family is the borage. The family of Convolvulaceae, which is also composed of hypogynous monopetalous plants, which has the bindweeds as its type, which are common in our fields and gardens. A species of the bindweeds furnishes jalap, an active purgative medicine. We also place in the class of Hypochloralae the family of Primocolaceae, the type of which is the primrose, the gentianae, and several others. The family of Sinanthierae, from the Greek sun, with, and anthos, flower, or compositae, which belongs to the division of monopetalous Epicurolae, is very remarkable for the arrangement of its flowers. They are generally small and united in a close mass called capitulum upon a common receptacle. They are of two kinds. One has a regular corolla in form of a funnel and called flosculus. The others have an irregular corolla, laterally warped in form of a little tongue. Finally, the anthers are united and form a tube, which is traversed by the style. Sometimes the capitulums are composed only of florets, like the thistle and artichoke, sometimes in demiflorets, as the dandelion and lettuce, and sometimes of florets in the center, and demiflorets occupying the circumference, as the sunflower and marigold. The first are frequently designated under the name of flosculus, the second are called semiflosculus, and the last radiate. Other monopetalae with epigynous corollae have the anthers distinct and form the class named Coryxantherae, which is divided into several families, among which are the Caprifolaceae, of which the honeysuckle is the type, and the Rubiaceae, a group in which we find the coffee, Peruvian bark, and Ipecacuanha, etc. The coffee tree appears to be originally from Ethiopia, whence it was carried by the Arabians to different parts of Arabia, but particularly to the province of Yemen, and especially to the environs of Mocha. Toward the close of the 17th century, the Dutch carried it to Batavia, and about 1710, one of these precious plants was sent from this colony to Amsterdam. It was carefully cultivated in a botanical garden, and soon produced fruit, the seeds of which furnished the means of its rapid multiplication. For one of these young trees thus obtained, having been sent to Louis XIV, flourished in the garden of plants near Paris, and afforded the French government the means of introducing its cultivation into Martinique. It soon spread through the West Indies and Brazil, etc. The trunk of the coffee tree is cylindrical and rises to from 15 to 20 feet high. Its branches are somewhat knotty. Its leaves are lanceolate, shining, and of a deep green. Its flowers are white and almost sessile, and its fruit is fleshy, ovoid berries, which are at first green, then red, and finally black. Each berry encloses two fleshy nuts, each containing a seed convex outwardly and flat within, and marked on the flat side by a longitudinal groove. This shrub ordinarily flowers twice a year, but there is scarcely an interval between these periods, so that it is always loaded with flowers and fruit. The latter generally ripens 4 months after inflorescence, and must be gathered with care according to its state of maturity. The plant which furnishes us the medicine called Ipecacuanha, used as an emetic, bears considerable analogy to the coffee tree, and is found in South America. The cinchona, or Peruvian bark, is so valuable in the treatment of intermittent fevers, is the bark of certain trees which also belong to the family of Rubiaceae. They grow in Peru. End of section 9.
Section 10 of The Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Elements of Botany by William Ruschenberger. Lesson 6, Part 3. polypetals, dicotyledons. This division is distinguished from the two preceding by having flowers, the corolla of which is composed of several separate petals. It is also divided in accordance with the insertion of the stamens into three sections called epipetale, epi, upon, hypopetale, hypo, beneath, peripetale, peri, around, which, in their turn, are subdivided into families, the most remarkable of which are the Umbelliferae, the Malvaceae, the Gearanicae, the Orientaceae, the Papaveraceae, the Caryophyllae, the Ampelidae, the Cucurbitaceae, the Myrtaceae, the Rosaceae, the Leguminosae, the Terebinthiaceae, etc. The family of Umbelliferae is composed of plants of the class Epipetale, the flowers of which are very small and arranged in umbel. One of the most remarkable genera of this group is that of the hemlocks, the poisonous action of which is very powerful. Several species are known. The spotted hemlock, Conium maculatum, has a cylindrical fistulous stem, longitudinally striated, branching and marked at its inferior part with irregular spots of a dark purple, which are also seen on the leaves. These are very large, three-lobed, and of a very deep green. The whole plant diffuses a strong odor, especially when rubbed between the fingers. This hemlock is biennial and grows in stony places near hedges. The carrot, fennel, angelica, anise, asafoetida, ammoniac, galbanum, and several other plants which are not at all poisonous belong to this family. The family of Malvaceae, the type of which is the marshmallows, belongs to the class of Hypopetalae. Its principal characters are a monosepalous calyx with from 3 to 5 divisions, and a corolla with 5 petals adhering at their base to the filaments of the stamens, which are united into a tube. The uniform character of the mallow tribe is to abound in mucilage and to be totally destitute of all unwholesome qualities. The most important plants of this family are the cotton trees, the fruit of which furnishes the textile, weavable material known under the name of cotton. Many species of this genus are known. One, called herbaceous cotton, varies much in its appearance. Sometimes it is a herbaceous annual plant, growing scarcely beyond 18 or 20 inches in height. At other times a shrub from 4 to 6 feet high, the stem of which is ligneous and perennial at its lower part. This cotton tree grows in Egypt, Syria, and India, and is also cultivated in Sicily. The arborescent cotton tree was originally from India. It is now cultivated in Brazil and Peru and constitutes one of the most important products of the United States. It grows to the height of from 15 to 20 feet. The leaves of these plants are alternate, petolate, and divided into 5-digit lobes. The flowers, borne upon peduncles in the axils of the upper leaves, are yellowish or purplish. The fruit is an egg-shaped capsule divided into from 2 to 5 cells, each of which contains several seeds. The cotton is found surrounding these seeds. The Gossypium herbaceum, herbaceous cotton, grows from 4 to 6 feet high and produces 2 crops annually. The first in 8 months after sowing the seed, the second within 4 months after the first, and the produce of each plant is reckoned at about 1 pound weight. The branches are pruned or trimmed after the first gathering, and if the growth is over luxuriant, this should be done sooner. When a great part of the pods are expanded, the wool is picked, and afterwards cleared from the seeds by machine, invented by Whitney, an American, called a cotton gin, composed of 2 or 3 wooden rollers of about 1 inch diameter, ranged horizontally close and parallel to each other, and the central roller being moved by a treadle or foot lathe resembling that of a knife grinder, makes the other 2 revolve in contrary directions. The cotton is laid in small quantities at a time upon these rollers, whilst they are in motion and readily passing between them, drops into a bag placed underneath to receive it, leaving the seeds which are too large to pass with it behind. The cotton thus separated from the seeds is afterwards hand-picked and cleansed thoroughly from any little particles of the pods or other substances which may be adhering to it. It is then stowed in a large bag, where it is well trodden down, that it may be close and compact, and the better to answer this purpose, some water is every now and then sprinkled upon the outside of the bag, the marketable weight of which is usually 300 pounds. Loudon. The flax, Linum usitalissimum, which employed in a like manner, belongs to another family of the same class, called the family of Geraniaceae, the type of which is the geraniums of our gardens and greenhouses. This well-known thread or clothing plant has been cultivated from the remotest antiquity for its cortical fibers, which, when separated from the woody matter, form the lint and tow, which is spun into yarn and woven into linen cloth. Flaxseed yields a valuable oil, by expression called linseed oil. Used in painting, in powder it is much used for poultices, and the refuse, after pressing for oil, forms a cake fit to fatten cattle and for manure. The stem of the flax is simple and cylindrical, from 2 to 3 feet high, and branching only towards the top. The leaves are sparse and lanceolate, and the terminal flowers are of a delicate blue. The calyx has 5 sepals, and the corolla, which is campanulate, is composed of the same number of petals, and encloses 5 stamens, and has many stigmas. The family of Aurantiaceae, or Hesperidae, which includes the orange and lemon, belongs to the same class as the 2 preceding, and is composed of trees or shrubs bearing articulate leaves, furnished with small vesicular glands filled with a transparent volatile oil. Their flowers are composed of a monocephalous persistent calyx, with from 3 to 5 divisions, and a corolla with from 3 to 5 petals. The style is simple, and the fruit is fleshy, internally separated by very thin membranous partitions, and covered by a thick pericarp, which, like the leaves, is furnished with vesicles filled with a volatile oil. The common orange, Citrus aurantium, is a tree which may grow to 30 or 40 feet in height, but in our climate seldom attains to 20 feet. It does not resist the cold of our winters, and during this season it must be protected by a proper temperature. Orange trees do not often yield fruit after they are 20 years old, but they may live for centuries. There are orange trees still existing at Cordova that date back to the time of the Moorish kings. One of these trees is said to be between 600 and 700 years old. At Versailles there is a bitter orange tree that, it is said, was sown in the year 1421 in the garden of the Queen of Navarre at Pampeluna. It afterwards belonged to the Constable of Bourbon, and after his death this tree, then the only one in France, was transported from Chantilly to the Chateau of Fontainebleau, whence Louis XIV carried it to the orangery of Versailles in 1684. The uses of the orange: the lemon, Citrus medica; the citron, a variety of the Citrus medica; the lime, Citrus acida; and the shaddock, Citrus dacumana, are well known. They all contain an agreeable acid, which renders them favorites as dessert fruits, or for making acidulous drinks, for preserves, confections, etc. The rind is generally bitter, and abounds in volatile oil. There are 2 principal varieties: the sweet or China orange, and the bitter or Seville orange. An agreeable distilled water is prepared from the flowers of the orange. The oil of bergamot is obtained from the rind of the fruit of a species of citrus. Most botanists place in this family the tea plant, Camellia, from Camelus or Camel, the name of a Jesuit botanist. This remarkable genus furnishes the domestic tea in universal use, and flowering trees and shrubs which are universally admired. There are 2 species, the Camellia bohea and the Camellia viridis, which furnish tea. This article is prepared with great care and considerable labor. The leaves are carefully picked one by one, dried in shallow iron pans over a slow fire, exposed to the air, frequently turned, and finally passed through a winnowing machine, such as commonly used by our farmers for wheat, etc. In this way the kinds of tea are separated, the lightest falling farthest from the fan. The first and heaviest is the imperial, next the young hyssop, then gunpowder, and so on. Both green and black tea are said to be from the same plant, but the green tea is longest over the fire. Ruschenberger's Voyage round the World. The viniferae or vites or Ampelidae form another natural family closely resembling the preceding, which belongs to the same class. It is composed of bushes or sarmentus, trailing or climbing shrubs, which support themselves by tendrils growing in the place of the peduncles, with simple or digitid alternate leaves, having 2 stipules at the base and small greenish flowers arranged in racemes opposite the leaves. Calyx very short, and the corolla composed of 5 petals and 5 stamens opposite to the petals. The fruit is a globular berry containing from 1 to 4 seeds. The common vine Vitis vinifera was originally from Arabia, but is now widely spread through the tropics and temperate zones of both hemispheres. The varieties are very numerous, and there are no less than 1,400 said to be cultivated in France alone. The fruit of the vine, the grape when newly gathered, and the raisin when dried, is extensively used as an article of the desert, and its juice furnishes wine by fermentation. Verjuice, a harsh acid juice, is obtained from the unripe grape. Currants, or Corinthian raisins, are obtained from a remarkably small variety of black grape, called the black Corinth. Wine is the product of the fermentation of the juice of the grape. Its color, as we know, varies from red to a very pale yellow. Red wines are made from black grapes, from which the pericarp or envelope of the fruit is not separated from the juice. White wines, when from white grapes, or from black grapes, the skins of which are not permitted to remain in the juice while fermenting. During fermentation there is a great quantity of carbonic acid disengaged, and when the wine is put into bottles before this process is terminated, this gas remains imprisoned in the liquid, and escaping the moment the cork is withdrawn, renders the wine sparkling and frothy. Champagne is of this kind. The family of Papaverdiceae also belongs to the class of Hypopetalae. The type of this family is the poppies, plants from which opium is obtained. The flower of the poppy is a calyx with 2 concave and very caudulous sepals, a corolla with 4 large petals, which before their expansion are plaited or wrinkled, a great many stamens, a 1-celled ovary which becomes an oval capsule enclosing a great number of seeds. The red poppy, Papaver, so common in our gardens, belongs to this genus, but the most celebrated species is the white poppy, Papaver somniferum, because the juice that is extracted from the capsules constitutes opium, a peculiar substance which has the property of calming pain and inducing sleep when taken in small quantity, but in a large dose is a violent poison. Dissolved in proof spirits, it constitutes laudanum. The family of Ranunculataceae, or crowfoot tribe, also belongs to the class of Hypopetalae. It consists of herbs or very rarely shrubs. The petals are from 3 to 15, hypogynous in 1 or more rows. The leaves are alternate or opposite, generally much divided, with the petiole dilated and forming a sheath half clasping the stem. The anemone, buttercup, monkshood, and traveler's joy are of this tribe. The plants of this family are in general acrid and caustic, and some are even poisonous. The family of Cruciferae is also composed of plants with hypogynous stamens. Almost all of them are herbaceous. The leaves are alternate. The flower has 4 unguiculate petals arranged in the form of a cross, and 6 tetragynamous stamens, 4 long and 4 short, and the fruit is a calyx. In it we place mustard, sinapis, cabbages, brassica, radish, Raphanus sativa, etc. The family of Racedaceae, the type of which is the Reseda or mignonette, that of the Violaceae, which includes violets, etc., and that of the Caryophyllae, which includes the caperbush, Capara spinosa, etc., and several other families belong to the class of Hypopetalae. The family of Leguminosae of the class of Peripetalae is next to the grasses one of the most useful, on account of the abundant and various aliment it furnishes for man and the domestic animals. Some of these plants are herbaceous, and others are even very tall trees. Their flowers are generally composed of a monocephalous calyx, ordinarily campanuliform or tubular, and a corolla with 5 unequal petals, the general form of which bears some resemblance to that of a butterfly. The stamens are almost always 10 in number, and joined together in 2 unequal fasciculi. The fruit is a cod or legume, generally elongated, compressed, bivalve, and has a single cell enclosing seeds which are ordinarily globular or lenticular. The leaves are almost always alternate, and the stem varies much. This very natural family has been divided into 3 sections: the Papilionaceae, Cassiae, and Demosae. The Papilionaceae are characterized by the papilionaceous corolla, and have in general 10 diadelphous stamens, as broom, Spartium scoparium, P. pisum sativum, Laburnum, Sitius laburnum, The Cassiae have an equal and regular corolla of 3 to 5 petals and 10 stamens, of which some are frequently abortive. Is the senna shrub, Cassia senna, the tamarind tree, Tamariandus indica. The mimosae have a double calyx, the external small and of 5 teeth, the internal monosepalous and tubular, sometimes called corolla, and numerous stamens, generally monodiphallous as the sensitive plant, Mimosa pudica. The gum arabic tree, Acacia vera, etc. The most common feature of the family of Leguminosae is, Mr. Lindley observes, to have what are called papillonaceous flowers, and when these exist, no difficulty is experienced in recognizing the order, for papillonaceous flowers exist nowhere else. Another and more invariable character is to have leguminous fruit, and by one of these two characters all the plants of the family are known. Many plants of this family yield seeds, the cotyledons of which are thick and fleshy, formed chiefly of facula that serve us for food. Others furnish gum, the different Acaciae, for example. Some are used as purgative medicines, such as senna and tamarind, and others yield coloring matters, which are very useful in the arts, such as indigo, capici wood, etc. Most of our fruit trees belong to the family of Rosaceae, the type of which is the rose tree. This family takes its place near the Leguminosae in the division of the peripetallous dicotyledons. The flower of these plants is composed of a monosepalous calyx, with 4 or 5 divisions, and a corolla almost always composed of from 4 to 5 petals regularly displayed. The stamens are generally numerous, the leaves are alternate, the form of the plant varies a great deal. We place in this family, which also includes many ornamental plants, the apple, pear, plum, cherry, peach, apricot, quince, medlar, almond, strawberry, raspberry, dewberry, etc. The apple tree, Pyrus mollis, grows from 15 to 20 feet in height and bears oval, dentate leaves, smooth on both sides, and white flowers tinted with rose color externally. It is indigenous to the forests of Europe, and in the wild state flowers about the beginning of May, but earlier when cultivated. The structure of the fruit has already been mentioned. More than 100 varieties are known. This tree only flourishes in temperate climates and succeeds best in a deep and slightly humid soil. It may live 200 years. The apple is a wholesome and agreeable fruit. The most important product from it is cider, a more or less spirituous liquor obtained by fermenting the juice of the fruit, which is obtained by pressing it. The pear tree, Pyrus communis, the tree similar to the preceding, is also indigenous to the forests of Europe. It succeeds best in rich soil, but also accommodates itself to dry and sandy situations. Pears are very much esteemed, and vary very much in taste as well as in form, and their fruit by fermentation yields a liquor very similar to cider called perry. The plum, apricot, peach, and cherry differ from the preceding in the structure of their fruit, which is a fleshy round drupe, slightly furrowed on one side, containing a nut enclosing 1 or 2 oleaginous seeds. The domestic plum, Prunus domestica, is a hardy tree of middle size, which accommodates itself to all kinds of soil. When left to itself, it grows straight and pyramidal, but from trimming forms a rounded top. The leaves are oval, smooth above and slightly pubescent below. Its flowers are white, and its fruit, the color and form of which varies, has a smooth skin, without down, and more or less covered by a very fine powder called flour. Nearly all the species of plums may be dried in the sun or in an oven and converted into prunes. The common cherry, Prunus cherrasis, analogous to the plum. It appears to be originally from Asia, and Pliny informs us that in the year of Rome 880, Lucullus, after his victory over Mithridates, introduced it into Italy. This tree delights in temperate climates and yields abundance of excellent fruit. The apricot, Prunus armenica, appears to be originally from Armenia. Everyone knows the fruit of this tree and the form of its stone or nut. The peach, Amygdalus persica, of which the nectarine is a variety, and the almond, Amygdalus communis and Amygdalus amara, belong to the same genus, but differ from the apricot in the nut, the surface of which, instead of being smooth, is irregularly and deeply furrowed. The peach is originally from Persia, and does not prosper except in localities where it is exposed to the influence of the sun. When carefully trimmed, it may live 40 years. The almond is a tree of 25 to 30 feet high. Its trunk is rugged and covered with an ash-colored bark. The leaves are straight, pointed, and dentate. The flower is white and expands before the leaves are developed. The fruit is ovid, elongated, a little fleshy, and of a green color, and the bony case which envelops the almond kernel is sometimes thin and pliable, and at others thick and very hard. There are two principal varieties, one called the bitter, and the other the sweet almond. Both contain a good deal of oil, and yield, when rubbed up in water, an emulsion called almond milk, which forms the basis of orgeat. Bitter almonds also contain, in very small quantity, a very volatile substance called hydrocyanic or prussic acid, which is a most violent poison. The strawberry, Fragaria vesca, is a herbaceous plant with a very short stem. Almost all the leaves are radical, and ordinarily consist of 3 leaflets borne on a long petiole. The column of the root gives rise to slender, long, rampant shoots, which take root from point to point, put forth leaves, and thus form new stems. From the midst of these leaves rise 2 or 3 simple, slender stems, which bear on their summit from 4 to 6 white flowers. The red fleshy body which succeeds the flower, and known under the name of strawberry, is commonly taken for the fruit of this plant, but is nothing but a prolongation of the common support of the seeds, which become succulent and very much developed. The true fruit, that is, the seeds in their envelope, adhere to its surface. This plant grows throughout Europe and in most places in North and South America. Raspberries, Rubus idias, which have nearly the same structure as the strawberry, are furnished by a shrub of the genus of bramble, which belongs to the family of Rosaceae. Botanists call the raspberry the bramble of Mount Ida, because it grows wild on that mountain, but it is also originally from the northern regions of Europe and America. It delights in a light and somewhat shaded soil. Its root is a ligneous stalk which produces several straight stems armed with numerous fine thorns. Flowers are white, quite small, and borne on slender peduncles. Its fruit is composed of many small monospermous berries, slightly attached to each other, and placed round a conical fleshy support. The dewberry, Rubus caseus, yields a fruit of similar character, but it is without the taste and perfume of the raspberry. The family of Cucurbitaceae belongs to the same class as the preceding, and is composed of large herbaceous plants, the fruit of which is a pepo. The pulpy matter found in the fruit of most of the plants of this family is wholesome, and often very nutritious. The melon or cantaloupe, so prized as a dessert fruit, is obtained from the Cucumis malo. The common cucumber is the fruit of the Cucumis sativus. Besides these we have the watermelon, Cucumis citrullus, and the squash gourd, etc. The family of Myrtaceae or Myrtae and several others also take their place in the division of Polypetales dicotyledons. To the same division of Peripetalae belong the Indian figs or Cactae or Nopalae. They are known by the stamens being indefinite, the calyx and corolla being imperceptible or very minute, and their succulent character. The fruits of many of the Cactae are pulpy and refreshing. The milky juice of some of the plants in this family is very dangerous, as that of the Cactus grandiflorus and the Cactus flagelliformis, etc. The insect called cochineal, Coccus cacti, is found on some species of cactus. End of section 10.
Section 11 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kattekliek. The Elements of Botany by William Ruschenberger. Lesson 6, Part 4. Diclinus dicotyledons. Footnote: Diclinus, from the Greek dis, to, and kline, bed. This term is applied to plants in which the sexual organs exist separately in different flowers, that is, not having both sexes in the same flower, being unisexual. End footnote. This fourth division of the dicotyledons is composed in the method of Eusseau, of plants, the flowers of which are truly unisexual and diclinous, that is,
The two sexes are not found in the same individual, but it is not very natural and is not adopted by the majority of the botanists of the present day. In this division we place the Euphorbiaceae, the Cupelliferae or Armentaceae, the Orticeae, the Coniferae, etc. The family of Orticeae is composed of plants both herbaceous and ligneous, the juices of which are often milky. The flowers are apetalous, joined in a catkin, or enclosed in a fleshy involucre, and have hypogynous stamens. The fruit is composed of a crustaceous achenium, enveloped by the calyx or involucre. We placed in this family the hop, Humulus lupulus, which is valued in brewing for the bitter quality of its strobili or cones, the banyan tree, Ficus religiosa, the fig, Ficus carica, nettle, Urtica dioica, the well-known plant which furnishes hemp, Cannabis sativa, mulberry, Morus nigra. The bark of the Morus papyrifera furnishes the paper of the Chinese. The breadfruit tree, Artocarpus incisa, the elm, etc. The hemp, Cannabis sativa, belongs to the family of Urticeae. It is a herbaceous, dioecious plant, the male flowers of which are arranged in axillary and terminal panicles, and the female flowers are sessile in the axils of the superior ramuscles. These flowers have a single envelope which takes the place of calyx and corolla. It is entire, oblong or conical, and in the female flowers laterally cleft, while in the male it presents 5 oblong and slightly concave parts. We know but one species of this genus. Its straight, quadrangular stem rises from 5 to 6 feet high. The leaves are digitate, acuminate, and dentate at the base of the stem, opposite and alternate above. In this plant, as well as almost all of the Diaecia, the males are not so tall as the females, and, through a singular error, they are always regarded by the ignorant as the female, and vice versa. Hemp is originally from Persia and has been as long in use as flax. It is cultivated in great quantity in different parts of Europe, and even grows there spontaneously. It is sown in the month of June in very rich soil. The female plants, which ripen later than the male, are chiefly cultivated for the seed, from which an oil is obtained, for burning in France, for eating in Russia, and painting in England. Within a few years, hemp has been cultivated in the United States. It is manufactured into ropes for rigging ships, etc. The elm is also a plant of the family of Urticeae. Its flowers, which are hermaphrodite, are very small and united in clusters at the upper part of the ramifications of the stem. They expand before the leaves, which are simple and alternate. This tree is indigenous in France and acquires a great size. It is frequently employed in forming shady avenues, and its wood is useful. The breadfruit of the South Sea Islands bears a pulpy fruit, which, when gathered before being ripe, is roasted. It tastes like bread made from wheat flour and potatoes. The inhabitants of Tahiti and the adjacent islands feed upon it nearly throughout the year. The family of Cupelliferae, or Amentaceae, contains several of our most important forest trees, such as the oak, beech, and chestnut. It is composed of trees with simple, alternate leaves. The male flowers are arranged in cylindrical and scaly catkins, and the female flowers are generally axillary and entirely or in part covered by a scaly cupule. The fruit is always a gland, which is commonly unilocular and always accompanied by a cupule. There are several species of oaks known. The common or red oak is a magnificent tree, which grows to a height of 60 or 70 feet. The leaves are laterally incised into obtuse lobes, and almost always regularly opposite. The male flowers form long, slender catkins at the upper part of the young branches, and the female flowers are sessile, and grouped in the axils of the upper leaves. This tree grows slowly, but lives for a long time. It rarely begins to bear glands, acorns, at an early age, but does not cease to grow till the end of 3 or 4 centuries. Its wood is very valuable on account of its hardness and durability, and is used for framework in building. Its bark, which is very astringent, is also very useful because it serves to make tan, a substance by means of which skins are tanned and form leather. Nutgalls, which are employed for making ink and for dyeing black, are excrescences produced by the sting or puncture of a little insect on the branches of a species of oaks in Asia Minor. The holm oak, or evergreen oak, which abounds in the south of Europe, has dentate leaves which remain throughout the winter. The same is true of another species of this genus, known as the cork tree, because it furnishes cork. This substance, which is spongy and elastic, is the herbaceous layer of the bark, which is removed from the tree every 8 or 10 years. There are a great many of these trees in Spain, and also in the south of France. The outer bark is the cork, but there is an interior bark which is left on to protect the tree, so that stripping off the outer bark is so far from injuring the trees that it's necessary for their continuation. Trees that are never barked are said to die at the end of 50 or 60 years. The bark is removed for the first time when the tree is about 15 years old. It is taken off in sheets, and after being detached, it is flattened by presenting the convex side to heat or by pressure. In either case, it is charred, slightly burned, on both surfaces to close the transverse pores previously to be sold. The carbonized surface produced by this charring may be seen in bungs for casks, but not in corks, which being cut in the lengthway of the bark, the charring is taken off in the rounding. The live oak, Quercus virens, grows to the height of 40 or 50 feet, spreading its branches, when in open places, extremely wide. It yields the finest and most durable ship timber of any species known, for which reason it is considered one of the most valuable trees in the United States. It is chiefly found in Florida and the southern states. The chestnuts, Castanea, form another genus of the same family as the preceding. The fruit is a species of nut with a single cell, which encloses 2 or 3 seeds containing a good deal of fecula, and is entirely enveloped by the cupule, the surface of which is studded with sharp points. The common chestnut is a large, beautiful tree which grows spontaneously in the forests nearly throughout Europe and different parts of North America. It sometimes acquires an enormous size. There is one on Mount Etna said to be 110 feet in circumference. It is hollow, and a little house has been built in its interior, with a hearth where they cook chestnuts, which are often gathered from the tree itself. In Cévennes, Limousin, and some other parts of France, the peasants live almost exclusively on chestnuts. The wood is used in building. It is extremely durable, and in high esteem for posts and rails to construct fences. The chinkapin nut, Castanea pumila, is a small tree, or rather a shrub, growing to the height of 30 feet in the southern states, but scarcely exceeding 7 or 8 in cold latitudes. The fruit is very sweet and agreeable to eat. The yoke elm also belongs to the family of Cupelliferae. The male and female flowers are arranged in catkins, composed of imbricated scales. It is a tree easily shaped by trimming, and for this reason is often employed in Europe for hedges. It sometimes rises to 50 or 60 feet in height, and its wood, which is very hard, is much used by wheelwrights and for fuel. A great many of European forests are formed of trees of the family of Coniferae, which is placed in the class of Diclinae alongside of the Cupelliferae. They are generally designated under the title of evergreens and resinous trees because they preserve their leaves through the winter and because their wood contains a great quantity of resin, commonly called rosin. Almost all of them have stiff, linear, coriaceous leaves. Their flowers are unisexual and arranged in cones of catkins which are ordinarily scaly. and generally the fruit also is a scaly cone. Fir trees and pines are types of this family. These two genera are distinguished from each other by their aspect, by their leaves, which are solitary on the fir tree and united in fasciculi or bunches of 2 to 5 on the pines, by the male flowers, the catkins of which are isolated and solitary on the pines and united and grouped on the fir tree, and by several other characteristics. Both delight in mountainous regions and on sandy plains. Pines abound especially in the north, where they form forests of vast extent. The stem is straight, and their height frequently colossal. A great many species are known. The Jersey pine, pitch or scrub pine, is of middle size, straggling growth, and full of resin. Its branches are tougher than those of any other pine, and might be used for many purposes if its wood were not subject to so early a decay. The pitch pine is generally known in its native country by the name of Norway pine. Sometimes, particularly among the Canadian French, red pine. It grows in close forests, is very tall, and its bark remarkably smooth and red. The timber is very heavy, for which reason it is rejected for masts, though its shape and size appear to recommend it for that purpose. The yellow pine is most in use for building houses as well as shipping. The loblolly, or old field pine, is found in large tracts in the southern states. All the woods seem to be filled with its seeds, for when any piece of clear land is neglected for any space of time, it will be covered by these pines. It is difficult, and in some cases almost impracticable, to recover land so run over, as the ground appears to have lost all fertile properties for other vegetation. The long-leaved yellow pitch or brown pine is a beautiful as well as a very useful tree. The white or Weymouth pine grows in the state of Vermont to an enormous size. It is the best timber in America for masts. Turpentine, resin, tar, and pitch are the products of several species of pines, and are exported in large quantities from the United States. The common fir is found in the same countries as the wild pine. Larch and cedar are very analogous to the fir tree. Of the uses of plants. From the short sketch we have just given of the vegetable kingdom, we see how many important and varied services are rendered to us by plants. Either directly or indirectly, all animals are nourished by plants. Indeed, there is an immense number of animated beings that eat nothing but vegetable substances, and those that feed upon meat would not find sufficient food unless they devoured each other without destroying those that are maintained on vegetable food exclusively. There is scarcely a plant that does not nourish some animal. Almost all insects, for example, live either in the perfect or in the larva state at the expense of the plant upon which they are habitually found, and even in the highest classes of the animal kingdom, the number of vitivorous species is immense. Footnote: Vitivorous, from the Greek phyton, plant, and voro, I eat, plant eating. End footnote. For the Quadrumana, the Gnorers, the Pachyderms, and the ruminants all observe a vegetable diet. Footnotes: Quadrumana, from the Latin quadrinus, formed from quattuor, 4, and manus, hand, having 4 hands. Pachyderm, from the Greek pacus, thick, and derma, skin. End footnotes. And man himself derives most of his food from the vegetable kingdom. Among the most important alimentary plants, the first are the cereals. Under this name we designate plants of the family of grasses, which afford nourishment to man and most domestic animals, namely wheat, rye, barley, oats, maize, and rice. There is in the interior of their seed, betwixt the spermaderm and the embryo, a considerable deposit of amylaceous matter. Footnote: Amylaceous, from the Latin amylum, starch, starchy. End footnote. Designed to nourish the young plant, and designated by botanists under the name of albumen or perisperm. It is this matter we use for food. We have already studied the history of these plants, consequently, it is useless to repeat it. We will, however, add here that the perisperm of the cereals, and consequently the flour obtained by grinding them, is essentially composed of fecula or starch, ordinarily mixed with a certain quantity of a substance named gluten, which considerably resembles animal matter. Wheat flour contains more gluten than any other, and for this reason it makes better bread and is more nutritious. Rye also contains it, but there is none in rice, oats, etc. Other plants also furnish abundance of fecula, but not from the same part as in those mentioned. Sometimes it is in the cotyledons of the seed, sometimes in tubercles, and at other times in the very substance of the stems or roots. Thus, peas and beans and some other plants of the family of Leguminosae furnish edible seeds, the cotyledons of which contain the same as the albumen of the cereals, a great deal of fecula, and a certain quantity of gluten mixed with sugar and some other matters. Whatever part this fecula may occupy, it in general constitutes, as in the pericarp of the cereals, depositories of nutritive matter for the nourishment of the young plant or of new shoots. The tuber of the potato owe their nutritious qualities to the quantity of fecula they contain. The same is true of batatas, the Spanish or sweet potato, a species of convolvulus, originally from India, which is now cultivated in all warm regions in the world. Footnote: Batatas is either a Malay or Mexican word. The plant is a native of both the East and West Indies and China. It was first carried to Spain from the West Indies and annually imported into England and sold as a delicacy. It is the potato of Shakespeare and his contemporaries, the common or Irish potato being then scarcely known in Europe. End footnote. The species of fecula known under the name of cassava or tapioca, of which great use is made in the West Indies, is derived from the root of the manioc, a plant of the family of the Euphorbiaceae, which also contains a very poisonous juice that is separated by means of water. Sago is another species of fecula obtained from the stem of a palm, and salep is also a fecula obtained from the stem of a monocotyledonous plant of the family of Orchidae. The most esteemed of our fruits, the majority of them at least, are furnished by the family of Rosaceae, for example apples, pears, plums, cherries, peaches, apricots, strawberries, raspberries, and to complete the list of fruit trees, we must not omit the mention of some species of the family of Ampelidae and the family of Aurantiaceae, namely the vine, the orange, and citron. Plants furnish us not only with wholesome and agreeable food, but also substances which are the greatest utility in the manufacture of clothing and in the construction of our dwellings. Hemp, flax, and cotton yield us long, flexible filaments, which constitute excellent materials for spinning and weaving. And our forest trees, almost all of which belong to the family of Cupuliferae, or that of the Coniferae, furnish abundance of wood for building our houses and ships, as well as for the manufacture of furniture and instruments of various kinds. Ornamental plants which decorate our gardens and conservatories are very numerous. They are furnished by very various families, in the front rank of which we may place the Rosaceae, because it has for its type one of our most beautiful flowers, the rose. Many species and varieties of rose trees are known, and almost all of them may be cultivated in the open air in our climate. They flourish best in a light soil and partial exposure to the sun. In the wild state, they have but 5 petals, in the midst of which we observe a great number of stamens. But cultivation has transformed most of these latter organs into petals and enhanced the beauty of the flowers. The dahlia, which was for some years so rare, but now everywhere met in gardens, belongs to the family of Cyanantherae. This beautiful herbaceous plant has a perennial root composed of bundles of horizontal, oblong tubercles, from which rises a cylindrical branching stem bearing opposite leaves and large flowers, which appear from the end of July till the approach of frost. The dahlia may be multiplied by its seeds or by the division of its roots. The genus Aster, which comprises a great number of beautiful autumnal flowers, including the Queen Margaret, which was imported from China into Europe about 100 years ago, also belongs to the family of Cyanantherae. The family of Caryophyllae presents our garden with different species of carnations or pinks, known under the name of common pink, China pink, etc. The family of Leguminosae gives us acacia, the sweet pea, etc. We have seen that a great many plants afford to man wholesome and abundant food, that others are violent poisons to him, but very many even of the latter are useful, because when prudently administered, they constitute powerful medicines. A great number of plants of the family of Solanae are of this kind. For example, belladonna, henbane, stramonium, tobacco, some species of the family of Papaveraceae, such as the poppies, and hemlock, which belongs to the Umbelliferae, etc., etc. In our citation of poisonous plants, we must not omit the mushrooms, the history of which we have already given. End of Lesson 6. Recording by Kattekliek. End of The Elements of Botany by William Rauschenberger.